So hello and welcome to our project meeting for 3D printing. And we start in time. And at first, some technical problems. At first, I want to explain a little bit this tool, this GoToWebinar tool. You have a possibility to raise your hand. Yes, if you raise your hand, then we can give you the mic and you can give us your question to us, or we have also the possibility here in the questions, English version, in the German version, under in Fragen, you can write down your question, and we look in this, and then you get possible after a little bit time you get an answer. Okay, that's are the first things, and we test this in this moment. So we start with a little introduction round of the participants, of the attendees of this meeting, and we start in this room here. First from my side, my name is Marko Matuszka, and I am the project leader of the 3D Softproof research project. This is the first part for today. And I'm an employer of Fogra. And now, yeah.
My name is Donatella. I'm here at Fogra as the PSR from the Peers project.
I'm Julie Klein, working at Fogra. Project used only last year, and I'm also working for this project.
My name is Andy Krauser. I'm the head of the prepress department and also involved, of course, in the two projects we are dealing today. For the online attendees, I would like to just call the names, and then you can just introduce you briefly, so simply unmute you, or we unmute you for the first time, and then you can unmute yourself, and I will just read the names, and then you can unmute yourself and just introduce yourself quickly. Alina Boranovic. So your mic is open. You can just start introducing yourself. You can do it later. Let's start with the next one, Berthold Oberhollenzer.
Yeah, hi, this is Berthold from Fogra, today attending from another room.
Okay, yeah. Loud and clear. We have Chris Bai.
Hi, this is Chris Bai from BenQ.
Good afternoon, Chris. We have Danwu Chen.
Yeah, hi, hello, good morning. I'm Dan Chen, and I'm an ESR researcher from Fraunhofer IGD.
And for those who don't know what ESR means, it's an early stage researcher, and this is an EU project where they have a lot of early stage researcher around the globe, and most of them are part of this meeting also because it highly relates to their topic. Also, we will come to that too. We will have then Fereshte Abedini.
Hello, this is Fereshte. I'm an ESR from a Peers project, and yeah, I'm working at Linköping University in Sweden.
Hello, we have Jonas Reinhardt.
My name is Jonas Reinhardt. I'm from Iowa, and I'm Switzerland.
Okay, welcome. Then we have Lubna.
Hi, I'm Lubna. I'm also an ESR in the Peers project, and I'm based at the Fraunhofer Institute in the 3D printing department.
Welcome. We have Marco from Southern Tyrol. Marcus Barbieri.
Yes, hello. Here's Marcus Barbieri from Barbieri Electronic Italy.
Welcome, Marcus. So we have then Matthias Moroch. Oh, you need to check your mic. This was like meeting the aliens and opening the mic. Michael Anton or Michael Anton.
Hello, can you hear me?
Loud and clear.
Okay, good morning. This is Michael from Stratasys. Yeah, joining this one from my home office. Good morning.
Good morning. Well, good to have you on board. Then we have Michael Marr from Fogra.
Hello, here's Michael. I'm also joining this meeting from Fogra.
Okay, then we have Mustafa Morsi. Mustafa.
Hi, Mustafa Morsi. I'm in charge of the Softproof implementation at Fogra for IGD.
Thank you very much. Ricardo Tonello.
Hello, I'm Ricardo Tonello, ECR 15 in a Pierce project from DTU Copenhagen. Good morning.
Good morning, welcome. Then we have Simeon Geiger. There are two logins, so we have a web and a non-web. I don't know exactly which access you are using. I can unmute also the web account. Now both access.
Okay, hello, here's Simeon Geiger from the ELM in Ulm, and I'm working as a researcher on the second project, which will be topic this afternoon.
Okay, welcome. We have Tanzima Habib.
Hello, I'm Tanzima Habib. I'm ESR 13 from a peers, NTNU Jorvik.
Welcome from Norway. Then you are.
Hi, this is Yoav Bressler. Do you hear me?
Loud and clear.
Okay, most people know me from the Appears project, but we have also a very long cooperation with Fogra. Usually my contribution to Fogra is that I print some sample and then somebody else measures them.
It's a very nice summary. Okay, thank you, Yoav. And then we try to go back. Alina Kronovic.
I have a question. I'm attending but having some microphone issues. So.
Okay, so you can let us know. You have also the option to write us a question using the chat or the question button. And then we have one more, Ali Ayami. Ali, can you hear us? Your mic is open, unless, again, if it does not work for some reason, just then use the chat or the question option to stay in contact with us. Oh, great to have you here. There will be a little bit more information from Marco about the attendance list, because there are some formalities, but I give the mic back to Marco.
Thank you. This slide, you see this in the web app of this the webinar. You find a chapter with handouts, and there you can download this handout, and then please fill out this in this way. I show you this as an example. These are the list of participants, and you only fill out the first line here. Yes, the name of your company, and then the legal form. And then the address of your company or your university or else. And then you mark the class of your company or university, then for example, you are a small and medium business, then you make the first entrance here. And if you don't know exactly here, it's described under one what this means to be a small and medium or medium business. And after this, you make in the participant, you wrote your name and the signature we do for you here on Fogra. And then, if you have saved this, then please send this file back to my mail address, and I wrote this down here. Send this to please send this to Matushka at Fogra.org. And
muted. Unmuted.
So let me just check again. Okay. For some reasons, there was a mute here. So for some reasons, Let me just check how long it was. Audio is back. Okay.
What was missing?
You just tell me, was it a question of seconds or we just, I can't hear anymore. Okay. We see. Sorry for that. Can you just give us a technical sign on what was the last thing you heard from us? So just again, please fill in. Okay, please fill in the file. Okay, so they basically you missed what is said on the screen. We do record the meeting. If you want to say something you don't want to be recorded, let us know. Then we can stop recording, and then the submission of the presentation will not be part of the recording. That is one information you missed, and I gave a little bit background on why we need it, and this is a formality from the Federal Ministry who supports this project. Okay, thanks for the update, and it's important to double check. Yeah.
Okay, then again, we also recorded our last meeting on our website, and you find this. You go to the Fogra website and select your language, and then you go to in the English version. A little bug here. You go to the English version, go to research, pre-press, research projects, 3D Softproof, and under publications. It should appear, but it does not appear. You have to change to German, and you see here our project meeting for the 3D Softproof project, and this is completely in English. This recording for this meeting is completely in English, and so you have a good background for today. Okay, then we start with the first research project. We start now, and it ends approximately, I think, 1 past 1, or what is the end of the?
12:30.
12:30, yes. 12:30. And then we make a short lunch break, and after the lunch break, at 1:15, we start with the second research project. So I give the mic to my colleague, Julie Klein.
Yes, so welcome. We will be talking, first we will give an overview about the project, about half an hour. And then Marco will show you the presentation of the Softproof setup. And then we will switch to the Fraunhofer Institute. They will show their progresses for the ray tracing renderer, for tone mapping, and for the ray tracing when the volume scattering is also taken into account. And then they will show their gloss measurements for the 3D prints, and we will end this morning with a small discussion. So the project here, it's about graphic to 3D printing, color accurate softproof for 3D objects, polyjet and multi-jet fusion processes. So the short name that we use is graphic 3D printing. The Fogra number that we use internally, perhaps you see this in the final report. For instance, it's a 12.017. The project leader is Marco Matusz, recently here. The project is running now since November 2018. So we have 1.5 years behind us, and we still have like 6 months until the end of the project in October. So it's together between Fogra and Fraunhofer Institute. What we'll discuss in the overview. Yeah. First, give a quick introduction in the full color 3D printing, and then the motivation of the project and the results that we were aiming at the beginning. We will discuss about the 3D Softproof workflow that lays behind the whole project, and then we will have an overview over all the work packages that are in the project. So first, the full color printing, what is it? It's a technology for additive manufacturing where the main point is the color of the object, is how the object is looking like. So it's not about printing something that has a special mechanical property. We want to have an object that looks like what we want. So we can have, we can use full color 3D printing, for instance, in a museum where we want to make a copy of some rare object that should not be, be damaged or something like this. So it should look exactly like the original. We are also talking about design when you want to make some example of design of your new shoe. You will not make the whole production of it, but you can print a 3D. You can make a 3D print of it to have the whole appearance of your object that you want to produce. You can also use it for like personal use. You want to give to your mother some mini version of you for her birthday, so it should also look really like you with the same skin color and so on. Or if you want for your wedding cake. And also something that is quite interesting is in the medicine. For instance, you are missing an eye and you want to have a new eye that is looking exactly like the other. So 3D printing can also be a solution here. So here it's all about the appearance. It should look exactly like you want. And appearance is first about the color, but also about the gloss. Is your object rather matte or glossy? It's also about the texture that is on the surface of the object, and also about the translucency. If we are talking about an eye, it's not completely opaque, but or here we have the teeth. They are also a little bit not transparent, but translucent. So appearance is it's all these properties that are going together with the color. So those are the main points for the 3D printing in full color. So the workflow, first you have to acquire some 3D data, or either you can use some 3D scan to acquire, to measure an object that is already existing, or you can also build an object in a software, in a CAD software, for instance. So here you can have also photogrammetry, like here, or you can also have a laser scanning device. And then this data is then saved into a given 3D data format. Mostly we use OBJ files. There are also other types of files that are used, but for the 3D printing, it's mostly OBJ files. And then you can open these files in different softwares, and you can look at the object. Sometimes you have to correct some errors that appeared during the acquisition, like if you acquire a person, you want to have not that their skin is smooth and so on. Perhaps when you have glasses, you have to correct something. So here you have the rendering and perhaps some correction. And after this, the 3D object is put through the RIP for the 3D print at the end. Yes. So in this project, we are dealing with two techniques, the polyjet and the multijet. Here we have first the polyjet modeling procedure. Here mainly with Stratasys and Mimaki in this project. So it's directly some photosensitive plastic that is printed, and then using a UV light source, the plastics are then remain there. So you have to use some support structures if you want to print a 3D object, and these 3D structures are here removed either with mechanically or with a water-based solution. Here you can use special inks that can have a different flexibility, or that can be more or less transparent. So these are the two, and here in the next slide we see when the objects are printed. Here you see some white yellowish structure around the object. So this is the support material that must be printed with it, and after it is washed and removed from the object. Then we go to the multijet fusion procedure, as it is used by HP. Here the object is printed either in a bath of some powder, some material, and then on the material there is here some fusing agent that is put on it that will lead the heat. And here, when you don't want to print something, you put some detailing agent that will inhibit the heat, and then applying some energy, the parts that you want to print here will be fused together, and the unfused part is just some powder that can go away without a lot of effort. So this is the multijet, and the other was the polyjet procedure. Yeah. So the main motivation for the research project is that 3D prints are quite expensive. The most of the price comes from the materials themselves, and that means when you want to try something, when you want to make them hard-proof, it becomes quite expensive. So here we have an example from the tube, who is making some mini figures of yourself if you want. Here we have the figure of 10 inches, so 25 centimeters, for about $400. So it's quite expensive.
But I think the 3D scan is included in this price. I think.
Yes. That's why the idea was here in the project to develop some softproof, so that you don't have to print your 3D object to see how it would look like, but you can look at it quite accurately in a softproof with the exact appearance that it would have when it is printed, really. So that was the motivation. Yeah. For the 3D. Okay, so we have a few problems with these 3D objects as they are saved here with the OBJ files. Also, the properties of OBJ are quite accurately defined. When you open one OBJ file here in Adobe Photoshop or in MeshLab, you get completely different appearance because each software reads the different parameters a little bit differently. So you have the gloss, you have the transparency that is most of the time not taken into account, and here you see the shadows. Of course, the whole environment is different. So we had last year at the Fogra master thesis from Tatiana Kancheva. She made some benchmark for these softwares, and she found a few solutions. If you want to show, for example, the transparency, what do we have to do in this software or in this software, or perhaps in this software it's not possible at all. So we had a few ways here to improve the way of displaying the OBJ files in the different softwares that we tested. Yes. And we have in the next example we have the here again an example with mostly with the transparency. Here it is in a 3D visualization software, and if we open this OBJ file in MeshLab, which is quite popular here in the middle, it's looking completely different. And on the right, we have the photography of the real object. So we see there is a lot of problems that are possible here. That's why, yeah, a ray tracing software was also part of this project. So the project goal was the 3D Softproof. So it's here we have a simplified overview of what it would look like at the end. The aim is to visualize on the computer what one object would look like, either for polyjet or for multijet printed 3D objects. Here you have the real light pulse with the real object, and at the end, both should look the same. So first, the object itself has to be characterized, and then the 3D Softproof station, the light pulse, has to be characterized, and the ray tracing on the computer, and at the end, the whole procedure should be standardized after this project. So the whole workflow, first some examples are collected to have an overview of what is used, what is required for this field, and then we have the polyjet and multijet fusion procedures for the 3D printing, and then the printing machines are characterized for their for the colors that they can produce, for instance. And then we have this 3D Softproof, as it is shown here, with the light pulse and the computer on the side to compare them. And we have the standardization, as we just talked about. And when everything is set, we can print some references and compare them really between the screen and the object itself. So here are the 14 working packages. A few of them have already been discussed last year for the PA meeting. And today we will talk mostly of, yeah, of these work packages from Marco or from the colleagues at the Fraunhofer Institute, and the remaining work packages for the 6 next months. These last one, of course, finishing with the final report. So now I will go through all the packages to to show a little bit what it's about. First, we have the web page that had to be developed. Marco already showed you before. You can here search in research, prepress, and then 3D Softproof. There is also a quick link, 3D Softproof, written as here, with big cases. So here we have the
publications of the PA meeting scripts, and in future, like say later, a few weeks, we will show the renderings from the software on this web page, on the new website.
On the new, yeah.
But this comes later from my side again.
Yes, you will have the okay. Then the work package 2. It's about having a database of 3D objects. Here we have a few acquisitions here from the Edge, from Marco here, or from Basket. So different types of objects were acquired with different 3D scanner, for instance, and all this work was supported by all these firms. We have Digit, Ulittle, Doob, and the AKA, and 3D Scan for You that helped to get all these data together. Yes.
Yes, and we have the comfortable situation that we have 2 3D scanners. We have a body scanner, and we have this
yes,
second scanner type, this movable desk.
Yes, these 2 are on the Fogra, the whole 3D, and the small desk. Yeah. So the work package 3 was about characterizing the light pools. So here we have an example of the light pools. So what is important in the light booth? First, spectrally, of course, the light that is used in the light booth. Here we can measure it with this device. And what is also important is to have the whole environment map. So one way to do it is to acquire some reflecting sphere from 2 different positions and the images together. So at the end you get some image of the environment map. So it's like what you see when you're at the center in all the directions, and this can be used then for the ray tracing after for simulating the acquisition of an object that is placed in these light booths. We have, of course, white references that we measure in the booth. And here what is important is that we set this CLAB L value of the light of the white sample to 98, so that we have a small value between 28 and 100 that can be used for the specular reflections afterwards. So we go to the work package 4. Here it's about profiling the printers. We want to characterize them and optimize their process. So here we have the example of some color chart that was printed here in a few different parts because it was too big for the 3D printer. It was here measured with different integrating sphere measuring devices, with spectra included and excluded. So these are the characteristics of the measuring device that we use. And afterwards, when we have this, we can have the whole gamut of the 3D printer. So it's shown in the next diagram. Here is the example of a print from the Maki 3D printer. Here we have the coverage in the LAB space. Here is L, here is P, and here we have the top view. So these are the color fields of the color chart that we printed. And then we can compare them, the gamut a little bit with, for example, the next one is, I think, with 3DP, yeah. So the points are from the Mimaki full color 3D prints, and the
3DP is a powder-based printer.
Yeah. How do you say purple?
Gamut volume.
Yeah, but the points are from the Mimaki, and the thing in the middle is from the 3DP. So we see the gamut that we can cover is much larger than the
shape of the color.
Yeah, thank you. Yes, and next we see also a comparison with the Fogra 39. Yes, here
the typical offset print.
Yes.
Simulates a typical offset print.
So you here see the points from the Mimaki are covering almost the complete part. Perhaps here a little bit less, and here it goes also a little bit further. So it's a good covering. Yes. And then in work package 5, it was about creating sample objects that will be printed later. So here, the example for the color chart that we just saw, those are created with MATLAB. You can give the shape and the spectral data that you want on each color field, and afterwards either, depending on the 3D printer. So we use Mimaki, Stratasys, and HP in this project. They are our partner, and we are working together. So depending on the 3D printer, the data that they want and the input is either sRGB data or using the cuttlefish
slicer.
Slicer printer.
Print driver.
There's a topic later about this cuttlefish.
So either with cuttlefish or with sRGB, we can give this data then to the 3D printers. Yes. Then we have the work package 6. It's about the monitor display. We will also hear a little bit more about this later. Here, transformation, also a little bit nice, okay. We will hear it, I think. Here it's just about the highlights, as I said before, that should be between 98 and 100 for the spectral reflections, and the Fraunhofer will talk better about this later. Then we have the work package 7. It's about measuring the BIDF of the test subjects. So here we have, on the one side at the Fraunhofer Institute, there is a goniometer, and on the other side here at Fogra, we have goniometer GON 360 that can make in-plane measurements, and we have some glass measuring instruments that can also be helpful for this. Yes, and when we have the measurement from the goniometric device on the next slide, we see that we can use some model to model the BIDF. When you look at the surface of the object, we have the light coming here. And let's say you look from this direction. The diffuse part here in red is quite constant over all the viewing directions. And in the specular angle, you have some specular peak that can be much or less large depending on the surface that you have. And for this, we have the Cook Torrance model to break the BIDF, which is in the next part. We have again the number the diffuse part and also the specular part. And we used this model to model.
Physical-based model.
Yeah, it's physically based. And we can use this to, when we have a few measurements, to model the whole BIDF of the object. That we can see on the next slide. Here the specular part. And then here we have our test objects, these green polygons. One is more glossy, the other is more matte. And we can see here on the left, when we have the glossy sample, here on the left side we have the measurement that we made, and here on the right you have the result of the modeling with the Cook Torrance model. Here on the left side, we have the observing layers. So here you see that there is the specular angle here giving the highlight. We have also the same example here, the specular angle for the matte sample. So the model is quite good for approaching the real measurements.
Yes, for detailed information, there we have talked a lot in the last project about this ansatz, and you can see the results there.
Yeah. So work package 8 and 9 that we will hear later from the counter. It's all about ray tracing, either without volume scattering in the first step, and then in the next step with volume scattering, where the light is also playing around in under the surface of the object. Here you have some some example of some nice rendering that is physically based, so not just to look like, but really to be true with NVIDIA. And then we go to the web package 10. So from here, the web packages are still to do in the next month. Here it's about psychophysical experiment to optimize the model parameters. So what is the idea? You can simulate with different approach function parameters, and you can also have the reference patterns that you have created in the work package 5, and you want to find visually what is the best set of parameters to approach the real object. So here we have then on the display on the monitor 3 models that are shown, and the viewer can play around with the parameters in order to approach best the real object. And in work package 12, it is about characterizing the material, not just using BIDF, but using ICT maps. So here we have first the BIDF measurements that we have and the model. And when we have the rendering parameters that we just talked about, we can put everything in an ICC Max profile to use it more commonly and for better exchange. So the next slide we can see, I guess, with so it's here we have the example from a white coated paper with here different viewing angles, and here different illumination angles.
It's a visualization of a lookup table. We see this later, such a lookup table that is a visualization of this.
Yeah, so in ICT you have only one angle, but here you have everything in the lookup table, and that would be the one of the results. Okay. And then work package 13 is then the comparison of the prints and of the monitor representation directly on the monitor. And here, what could be used? The industry standards softwares like MeshLab and so on, and the project software, the rendering, the retracing software that is developed by Fraunhofer Institute. Yes, and work package 14 is the final report. And then I'm done with the overview.
Thank you. Are there any questions? When you have a question, you can raise your hand. For example, yes.
No, there's no question so far. Zoom you out, so I love to play with my camera here to get an atmosphere here in our Fogra lab. Okay, this was a high-level introduction to get everything up to speed and on the same status. If not, we can maybe go back to the agenda and just see where we are, or just directly speak. Wir haben die nicht approved, die Agenda. Just to see whether anyone is fine with the agenda for the day, and to see whether we should add something, or is there something missing you would like to add or something, or to change the sequence of something because we have to leave or something like this. So you see it. What's this? So we are good in time, and
we have 3 minutes.
And in ISO, you know, there's a nice unwritten law, which means silence is content. That means if you don't say anything, you are 100% happy with what we are doing. This is quite a good basic rule. So silence is approval, in other words. So that makes it also easier for us to proceed here. Okay, but you got this agenda anyhow, and we just move on the next one.
Next topic, yes. Talk about the Softproof setting, and for this, an online meeting limits the possibilities to show this because it's a visual appearance thing, and so we can only show you comparisons, but you don't see the result. Right, because your screen has no color managed and so on. It's too complicated to make this remote. So, yes, the same thing as Julie started in 3D printing. The appearance is a little bit more complicated as in the conventional printing. So, you have to specify to get a correct appearance of an object. At first, that's an object, and then you have an environment of this object. And you have to fix this environment to describe and see. And then this environment interacts with this object, and the photons from this object, and this light from this object, can be reflected on this surface. And the first thing we talk about is the diffuse color of such an object. This is this color what you typically measure in the conventional printing with measuring with a spherical measuring geometry, or with with 45-0 measuring geometry, like an FD7 or an I1 Pro or with the spectral LFP from Barbieri and so on. And the second thing what can be happened is that, well, you see that in the specular direction, you have for a photon what goes to the surface, and in an angle you have a specular angle, and this specular angle you have a peak for a glossy surface, and we mean this the glossiness of such a surface, and you can measure the peak of such of this peak, or you can the shape of this specular peak and so on, to characterize the gloss. And then for the 3D prints, very important, you have a transparent material, and so the photons can go inside the material, through the material, and can be scattered in the material. And with this, we call this translucence, for the light transport in the object. And this is split in the scattering and in the transmission of the light in this object. And the third part, fourth part, is the texture. This is the variations of these influences on the object. And now we have to catch up these points to get a correct appearance of such an object. Where we have
just one comment from Mustafa that it said 3.4 is included in 3.3, so we don't need 3.4 separately. This is 3.4 is included in 3.3 on the agenda, so there is no separate need for doing that, but we can then handle it when we come to 3.3.
Okay. Yeah. Now, after this top level into the abstract introduction, you see our Softproof setting and what we want to achieve. On the right-hand side, you see our norm light, one norm light cabin, and our camera in front of them. And on the left-hand side, you see a screen. And in this screen, there's the rendering of a 3D object, a 3D model. In this case, Minaki print. We have the OBJ model of this, and then the renderer makes this rendering of this object, and then we compare the real object. It doesn't work well. Okay. And when we compare the rendering with the object, instead we use for this the camera picture of this object. So, and in this setting, there are a lot of possibilities to do something wrong. And we start on the right-hand side with the characterization of the norm light cabin to make a good soft proof here. Yes, we use a cabin which is certified according to ISO 3664 2009, and we use for the calibration, or for the not for the calibration, for the settings of this norm light cabin, we measure barium sulfate, which has a reflection around about 98%, and we measure with our spectroradiometer such we have a luminance of 160 candela per square meter on this on this surface of this biome. And this is our setting for this home light cabin. In this case, there is an intensity of 30% of the maximum range of this home light cabin. And we need this, we do this in this way and not wider, because we have to render this on the monitor, and the monitor, our monitor is limited with the maximum of luminance. And so at first we start with this 160. This means the diffuse reflection of this this biome sulfide is a diffuse reflector, and so the diffuse reflection is at 160 candela in this moment. The second part is the characterization of this environment, the relative characterization of this environment. You see on this, we have a mirrored wall in this cabin. And you see on this mirror wall, you see the reflections of the reflection spots of the light. And now we have to see where the light comes from and go to the object. And for this, to describe this, we use, we make two photos, two HDR photos, high dynamic range photos from the mirrored wall. See the result here. These are two high dynamic range photos of this wall, and you see directly the influence of the in Softproof. The person has an influence of the result of the Softproof.
She is part of the environment.
Yes, it's part of the environment. Yes, don't change the person. No.
It's close.
And if you switch the light on in your room, then you have a completely different environment.
Every photon the sample is seeing has to be taken into consideration.
So, and it's not perfect, this HDR images, because you see this on the left side. The right side is good. The left side, you see the black spots above the highlighted spots. So small error in the merging this HDR photos. And from these two pictures, we can merge them together to get the environmental map of the low light cabin. This looks so. And this information about this relative intensities of the illumination, we give the ray tracing renderer from the Softproof. Okay, that's okay. This was the characterization of our low light cabin. Are there any questions about this approach, or not? Because we have no feedback here in a remote meeting from the participants. Not so easy. Okay, I think not. Then we can go ahead to the material description. For the renderer, we've seen the lookup table from Julie Klein is a good visualization of this. Our renderer takes the environmental map of this room light cabin, or light proof, and in this lookup table you describe your material. And this material, at first you have the first four lines are the CMYK values. In this case, we want to, at first we start with the rendering of the biome sulfide, so the material does not play a role. We make 0 to 155. And then the fifth line, you see the illumination angles. And in the sixth line, you see the detection angles. And then you see the reflection of this object. And for simplification, we start, it's not true for barium sulfate, but we start at, for the first approach, we can improve this later with 1. Yeah. We say the barium sulfate reflects in all the detection angles and illumination angles in all every spectral for every wavelength 1. I think there are 2 degree 10 yes from 380 to 700 nanometer. It's with a quantization of 10, I think. Lookup table. And this is a this is a text file. In future, we change this to the ICT max profile. But for the researchers, it's a little bit easier to work with this text file. So, and with this material and the environmental map for our moonlight cabin, we can create a rendering of a 3D model of our barium sulfate. And now we compare this 3D model here. Oh, no, sorry. We save, and from this rendering, we can save an in spectral image of this rendering. And this spectral image you see here, or one wavelength of this, the white channel of this spectral image as a gray image. And then we pick from this barium sulfate, we pick an area on the surface. Oh, sorry, that's a little bit confusing now. And we pick a little area on the surface of this barium sulfate. And then we can compare this. We can compare on the right side this barium sulfate and this picked area with our total illuminance of 160 candela per square meter. And then we get a correct scaling factor, and then we can rescale this spectral image to the correct intensity. And we can compare this to our barium sulfate in with a photo of our barium sulfate in the moonlight cabin. And you see the result here. There a small difference, a small color difference, because we do some errors. Yes, at one point we work wrong is on the right side we use a reflection of totally 1. This is not, it's not correct. Yes, it's too much. It's 2% too much, and we see this in this L. And we have also used for this photo and camera calibration. And we have we create an ICC profile for our camera in this moonlight cabin. We switch off the light, but for this photo we have switched on the light. You see anything? I switched off the light in the room, not in the moonlight cabin. And so we make also there an error. And it is not completely the same. We can improve this in this way that we can use the right reflections measured with our toniometer from the barium sulfate, and we can readjust this with the influences of the room and so with the CS2000 to get a better result. But this is the first starting point, and from this we get in the constant for the correct scaling or for the correct white balancing from the renderer to the moonlight cabin. So now we come to the first results from this rendering. We start with an easy object with the printed part from the multi-jet fusion printer from Hewlett Packard. Well, you can show this in the camera, I think. This is more or less Lambertian. So the more Lambertian like like the Mimaki prints or the Stratasys prints. You have not a specular reflection or not a big specular reflection, and so it's a little bit easier to measure and to render this. And on the left side, you see this. We measured with our toniometer. We have in 45-degree illumination, and the detections are rendered there. And on the right side, you see a picture of this object in our normal camera without the ICT profile of the camera. And now we compare this. From this goniometric measurements on the left side, we create a lookup table, like the lookup table from the barium sulfide, and with this lookup table, we create the rendering and the environmental map and our white balancing. Yes, we create this rendering, and then we compare the surface of this object from the left side to the right side. Or we move this to the LRB color space to get a more appearance-based difference, like in X, Y, and Z, and measure this, and we see we have a small color difference on the surface. There are problems left. Yes, you see the shading works not so well. For this, we have to improve our method to creating this environmental map to get this correct. And so, but the diffuse color on the surface, on the top of the surface, looks wrong this time. So for the proving that it is not a one shot or it's randomly, yes, I do. Sorry, at first we make the same. From the last meeting, we have seen the Coq-Torrance fit. We can also make a Coq-Torrance fit of this for this prints here. And this works not so well at this time. I think there are problems with the lookup table and not with the Coq-Torrance model. We get a refractive index on 1.52. There we have to fit this refractive index by creating this Coq-Torrance fit, and this is our fit. We have to double check this Ulm if this is correct or not. And you see the rendering, it's too dark. Yes, then we have to improve this. That's not perfect, but I think this should work in future. The second, that is not randomly. The second approach, the same approach for the green object. Yes, on the left side you see the photo made with our camera in the setting, in the profile. On the right hand side, we use the white balancing we get from the barium sulfide and rescale this, and then we get an error for the measured value, for the measured and interpolated values of 2.2 2000 on the top of the surface. Also, okay. Now we go to the samples from Mimaki, and from this objects we have a glossy version and a matte version. This comes from this fact that we changed the orientation in the building space of this object in the Mimaki printer, and it works also well. You get an error. We take again the photo, and on the right hand side we make the lookup table and measure it with the goniometer and make an interpolation, and then you get also a small color difference of this Mimaki prints. Yes, now to the classic part, and this works at this time not well. Yes. On the left side you see the magenta object. You can camera the high specular reflection is high of this object, and left hand side you see the object from the camera on the right hand side with the rendering with the lookup table, and this time ship it with the Cook Torrance model, because it's not so easy to interpolate with specular reflections, because we have no measurements around 0 degree. There, our Johnny meter cannot measure 0 degree illumination and 3 degree detection. It's not possible with this.
With the setup.
With the setup, and so we have the interpolation. The interpolation is not good, but the Cook Torrance model at this time is also not so nice. But we will improve this because the renderings from the last meetings looks good. Yes? But I think there is some problem with communicating between the Cook Torrance model, the lookup table, and the renderer. There are some problems, possibilities of issues. Yes. And we have to check this, because you see here the color differences from the left-hand side, you see the measurements of this magenta object. On the right-hand side, you see the fit with the Torrance model, and you see delta E difference is smaller than 5, except the angles after the specular angle. And so we have to check what's happened there. Here you see the result for the interpolation, and you see the problems. You see on the right-hand side, the color is okay, but the specular reflection is in this case yellow, so we have not a chance to interpolate this correctly, or I don't know what's the error there, but we want to, in future, we want to solve this problem with the specular peak. Okay, this for the rendering, but you see here the result of the interpolation. Yes, it's not so good like the Cook Torrance model. So we yes, we have to check this why we get some worse result. Okay, now to the point with this glossy samples. If everything is okay, there we are using the same. We have a perfect rendering with the correct render, with the correct lookup table and so on. We don't see the specular reflection at this time, because in this setting here, we use in monitor or for the diffuse or for the packet parts, HP parts, we use in monitor calibration with 160 candela, in luminance of 160 candela per square meter, and our specular reflections are really higher than this specular reflection of this barium sulfate. And so we have to adjust this setting now. But for the diffuse parts, we can use this setting. Yes, we take our screen, we make an luminance of 160 candela per square meter, and we do the lookup table. So, and then it's only a homework to get the characterization of this. You will have this HP printer. For the specular reflection, you see this problem here on the left side. Yeah, this is a linear scale. This looks a little bit stupid, but this linear scale on the 0 degree. You see the diffuse reflection of this object, and then you see the specular peak of this, the very high specular peak, and we have to find a method to use this, or to catch this with the correct appearance of such an object, of such a specular reflection. And to do this, we have to scale this physical-based scale, and this it's called tone mapping. So we have a measured value like this, from the Johnny meter. Then we give this with the lookup table to the renderer, and we get a result from the renderer. And this is at first the specular map is a physical-based scale, linear scale. And then we have to map this with the correct perceptive model, which I think it's a logarithmic model or else to get the correct appearance of the specular highlights. And the way to do this is here, or we take a monitor profile now with 200 candela per square meter, and we do everything the same for a luminance of 160 candela per square meter. And if you have reflections under this barium sulfate, then we do everything the same like for the diffuse planes. And half for specular reflection above this, of reflections above this 160, we make this HDR tone mapping in logarithmic scale. There are a lot of strategies to catch this, and we use a global strategy. Global means in this case that we have no connections between the environment of such a pixel in global map for the whole picture, and we want to do this not nice. With most a lot of these HDR tone mapping approaches should look nice, and we don't want nice. We want realistic. This is the big challenging thing here. And for this, we are a little bit too late, and we are behind our timetable, and so we have to do this now in the next weeks, and I will present you the results of these renderings of our new web page. I think in 2-3 weeks we are ready to start with this new web page, and there is then an entrance or a possibility to see these renderings, and you can make a download file there, and I will present you in future here the results of the implementation of the Cook-Torrance model, the HDR tone mapping results, and we have also not spoken today about this, the printer characterization with handled instruments like the Canon reflectance analyzer for the gloss, or the from Konica, the gloss device.
Reflectance analyzer?
No, from Konica.
RowPoint IQ.
RowPoint IQ, or the spherical measurement device, and so on. And we can combine this, and we want to make an easy version to characterize like this Hewlett-Packard prints, HP prints. And inside there, because at this time our measurements and our characterizations depends on the volumetric measurement, and they are very, very tiny. Okay, and something more perhaps. Okay, that's all from my side. There are any questions or comments or ideas?
Again, these are intermediate findings. This is not final, just as an update. There are some points where we know this is problematic or we need to check, but this is kind of an intermediate findings of our setup and our results. What ray tracer was used for rendering? Yeah, this is a perfectly question leading us to the next point. And that helps us making Mustafa now presenter. And so we can ask him to update us on point 3.3 of our agenda. Mustafa, are you ready? We have now a few more attendees, like Philip Orban. Let us briefly unmute him. Philip, can you introduce yourself briefly?
Yes, can you hear me?
Loud and clear.
Perfect. Okay. So should I introduce myself or what was the question?
Because you missed the introduction at the beginning, yeah.
Hello?
You missed the introduction in the beginning. That's why I asked you to introduce you briefly. Can you hear?
Hello?
Yeah.
I can not hear you.
1, 2, 3. So Mustafa is right now the presenter. So okay.
Mustafa is muted.
Now you have a problem with your mic, Philip. Okay, let's go back to Mustafa and we catch up with those who are left behind. So Mustafa, just go on.
Hello, so this is the progress report for the PA meeting. I know we went over the motivation, but I want to go over it again. So soft proofing allows the users to make informed decisions. As we've mentioned before, test prints are costly, mostly materials, but also in printing time. For bigger materials, prints can take up to 12 hours, maybe sometimes days. Soft proofing is a standard in 2D, but it's still a challenge in 3D printing. If we use just gamut to sort of get a simulation, you can see on the left here, that's a print. The model is just viewed in Blender, which is a popular modeling application. So maybe the in Blender or scanned and edited in Blender. If you just use gamut mapping, you get the image, but when you finally print it, you get something that looks different because there are more effects that need to be simulated. So what we have here is we have a known 3D file where we have know the RGB texture. We also know the ICC profile of the printer. The ICC profile should include the spectra value at the grid points of the profile. We know the radiance, because we're using light boosts. So we capture the environment map, but we want to know is what the camera would see. So it's basically to simulate what it would look like if it was actually printed. So this is the plan. I'll quickly go over each step. First of all, what is ray tracing? Well, we have a screen, and the screen comprised of pixels. At each pixel, we shoot multiple rays into the scene where we have our 3D printed object. Once the ray hits the point at the object, we calculate the BRDF, which is a bidirectional reflection distribution function, which I'll explain later. At each point, at that point, and we do that by shooting multiple rays into the environment map and getting the lighting information from there. For ray tracing, we're using an NVIDIA Optics path tracer. It's a library designed by NVIDIA. It's robust and flexible. It's used by a lot of companies, and it allows us to use GPU acceleration, especially the new GPUs created by NVIDIA in the last couple of years, the RTX series. And it allows the use of arbitrary geometry and ray head shaders, which we use to implement the environment maps. So for this renderer, we convert everything to spectral measurements, which are percentage of reflection between 400 and 700 in 10 nanometer, so 31 values. 400, 700 is the visible spectrum, so that's why we choose that. We start with the colors in sRGB. We use the printer profile to transform that to CMYK gamma. Gamma is our internal measurement of translucency. Then we use the spectral measurements we have in the ICC profile to convert these to spectral values, and these are used all throughout the ray tracing. That's good because it allows us to do different things, allows us to use lights with different spectral distributions, so we can use a standard illumination like D50 or D65 or even a measured illuminant. And then, unlike using other color spaces, there are no perceptual considerations in the space, so it's linear and it's physically based. We're basically trying to simulate what happens in real life. So basically what we do is we do the steps we said before, but repeat that basically 31 times conceptually. Of course, we don't actually repeat that. We do them all at the same time, but just to give you an idea. Something optional and that's not implemented, but can be done with the current setup is that you can combine multiple environment maps to combine multiple illuminance. So say you have a scene where you have a tungsten light and sunlight coming out of the window. You could capture each light individually in an environment map, and then we would be able to combine them to create what would the object look like under mixed illumination. As mentioned before, for lighting, we capture environment maps. So HDR images are currently not standardized, and there's no set method for capturing them. So we've tried to set a somewhat standardized pipeline. We use the same tools, which are open source and available to create environment maps that would be consistent. On the left here, you can see the last environment map that I captured, and it's for a 2D printing booth, 2D viewing booth, sorry, and it's not perfect because the lights are only from the top, but we hope to use environment light booths that are illuminate the object from all sides. This is a lighting booth that's created by another department at Fraunhofer IGD, and I will be next week. I would be capturing the environment map for this light booth, and would be using that for the rest of the research process. As mentioned, we would have to scale the rendering the previous, so I'm just going to skip this because Marco just explained it. What are BRDFs? It's basically a function that tells you for each angle of incident light, how the percentage of light that would be reflected in a given observance direction. And you do that for all directions in a hemisphere. And this can be used in the rendering to tell you what the object would look like. So we could measure a BRDF, which is what Fogra has done, but as you said, they had problems with certain angles and you need a lot of measurements. So that's why another alternative is to use BRDF models, which are just use of numbers of equations with a couple of parameters to describe a surface. So like the Cook-Torrance model is an example of the Cook-Torrance model is an example of a BRDF model that we have implemented, and it basically uses, I think, 2 parameters to describe the surface, and then you would have the surface. So to fit the BRDF model, we have a plan that's currently in progress. So we would have this calibration object. We would have a rendering and an image in the light booth. And we would want to, we would want to align them and then use them to estimate the perfect BRDF fitting for the BRDF model that would simulate the actual appearance of the object in the light booth. So first we would capture an image of the calibration object in the light booth. We would also render the object with using the environment map from the light booth. Then we would align the rendering and the image. We're evaluating a library called VisionLib. Currently, I will show you a video about it, next slide, to do the alignment. Then we would compare the rendering and the image, and then iteratively we would adjust the BRDF parameters, render the color object, compare, and repeat until we have a fit that's good. So this is the library I mentioned. So it's used a lot in the automotive industry. So that's why most of the examples will be cars. But as you can see, in real time, it can basically match a CAD object to a picture or a video stream. So that's why we want to use it, basically just to get the alignment part. But it does have other features. finally, the last step would be to simulate the effects of the printing process. So the printing process is not perfect. You have a few different effects that cause difference in the final print. So first of all, the materials are translucent, which leads to the blurring of textures. You have the printing resolution and the halftone leading to different artifacts. And we have different strategies for combating that. So first of all, we would simulate the effect of the lateral light transport and the halftone by actually just blurring the texture in a pre-process before simulating it. We would also try to change the surface normals to an extreme angle to simulate the staircasing artifacts. This is similar to bump mapping, which is a technique used in real-time rendering and video games. We'd also smooth the geometry to reflect the effect of the printed system's limited resolution. If you get a 3D model and zoom in any renderer, you would start seeing the tessellation, which you start seeing really small triangles, and you don't get that with a 3D printed object. So you would need to smooth the geometry to get rid of the triangle tessellated effect. And now for a demo, I might have to stop sharing my screen and start sharing it again. Yeah. Okay, so this is a scan 3D figure. I'm not sure how good you're seeing this.
Is it Mr. Bean?
No, actually, wait, it crashed. Yeah, okay. So this is a figure. It's a scanned, I think it's. So that's one, I can rotate it. So the vase I showed in the beginning, I also show that. It takes a little while to pre-process the data, but it's still much faster than actually printing the object. As you can see here, this looks much closer to the actual print than the simulation that's in the first slide. So if I bring these together, you can see it looks much closer to the actual print than the gamut mapped version. Of course, this is still not calibrated, so we still work on that. But yeah, and you can have, and finally, I'll show the head. No. Wait. Yeah, okay. So this is the head model that basically most of the research was developed on this head. It's my standard test model. Can you see the simulations I'm viewing?
Can we see what?
The simulations, the demo I'm doing. Can you see the head right now?
Yes, yes, yes. And you see if you in the webcam, you see what we see. You know, we share our.
Yeah, okay. Audience views, because it's giving me like a red bar for 100%. And when I wasn't doing the video, it was.
Yeah. So now you see what we see here even better. You see?
Yeah. Okay. So. And as you can see, basically it converges quite fast to an image. So if I start this over again, it takes a few seconds to pre-process the data, but once it's done, it quickly views the picture and then simulates it, and it converges quite quickly. So you could have a soft proof in about a minute max. If like worst case scenario, if it's like a really big texture and a really big object, it would be about a minute. So it's much faster than actually printing an object, and obviously much cheaper. And that was the progress update. Any questions?
That was quick, Mustafa. Thank you very much.
Yeah, sorry. I
As
speak too
always,
fast.
high density. Very good. Okay, question to anyone? Are there questions for Mustafa? Or maybe Philip, now your mic is working, I see, or is it?
Yeah, I had a few problems just when you asked me to do something. I think it was like introducing myself or so. I don't know. Can you hear me?
Right. Yeah, loud and clear.
Okay, excellent. Yeah, it's basically what I want to emphasize is that we are planning also to take this booth that Mustafa showed and measure the environment map for the booth, because the booth that was shown in the pictures has a much more uniform lighting environment than when we use a normal viewing booth that is basically dedicated to judge 2D prints. And for the 2D prints, we have these sharp shadows, which is very unrealistic. But here, this basically made this booth as a rotation stage beneath, and it is made for 3D scanning of objects. A small booth made by our 3D scanning department, and this is, I think, perfect for simulating the objects, so the environment map, and also comparing pictures of objects with the rendering.
Okay. And as we try to say, we would like to start from easy to complex. So to start with very diffuse materials and get a whiteness and a lightness match. Then with this easy example to go more on the grayscale, and then the specular objects to just add step-by-step complexities. Because if you start with some very complicated, even fluorescing objects, this would be too much. So this is our approach, to just go step by step from easy to complicated surfaces and try to find issues in the involved characterization, modeling, and ray tracing. Okay.
I think also maybe one aspect that might be interesting is of how well these BRDF models are really representing the real BRDF of the objects, which means that because what we do here in order to ensure that the is well reflected by the rendering is that at least for the measurement geometry, this 45.0, the BRDF model parameters are tuned to match the measurements in the profile. But of course, when it comes to the specular components, then typically the BRDF model has some error compared to the real BRDF. And this would also be interesting to just investigate for the typical printing materials. How far away is the model from reality?
Yeah. But this is what we know from 2D soft-proofing also, that you have maybe a measurement-based match, but you need to defer from a measurement-based match to get a visual match. This is still open issues to track them down, the reasons, but this is what we see here, to also put the visual assessment and the perceptual match in favor, and then see how the means and the measurements fit. This would be interesting, yeah, to see if the fit gives a good result, but then you have a misfit with some points on the BRDF measured, claiming the ground truth, yeah, and you have some data which is out far away from the ground truth, but giving a better result. Yeah. Okay, thank you very much, Mustafa and Philip. Are there any questions? I just seen that we have Mr. Alvin Kiene here now with us. So Kiene, can you introduce yourself briefly?
Hello, sorry, I couldn't understand you. Could you repeat?
Can you briefly introduce yourself because you missed the introduction call of expert at the beginning?
Okay, so my name is Alvin Kienle. I'm with the Institute of Laser Technologies in Ulm. Yes, okay. And I will give a presentation this afternoon.
Perfect, perfect. I just want to make it formally correct that everyone is introduced here in our. And if I missed one, just use the raise hand symbol or ask us a question, then we can unmute you. And again, our system is in a way that once we unmuted you one time, you can unmute yourself. It's just the first time where we have to unmute you. Okay. Then we go back to our agenda, Marco. Do you make your presenter on your own, or should I? I can make your presenter.
Oh, okay. Then we have this point about this BRDF measurements. We have a small presentation about this, Philip?
It was already part of this, the one, but we can also.
Okay. Then
yeah, I think we can open because this is a quite interesting idea. We can open the presentation at this point. Mustafa, can you open the presentation again? Exactly. If you maybe go to the slide before this slide. Okay. So I think one of the we thought a little bit about a very practical way to measure or the BRDF models. We are not really measuring the BRDF, but we are aiming to fit the BRDF model. And of course, what is possible is to use some usually very expensive devices to measure BRDFs at distinct points and then to fit a model to these measurements. But if you want to use the system in your company, for example, then it is quite, it's challenging to get these measurement devices for like multi-angle measurement devices. It's expensive, it's time consuming. And so our idea was that this is even not really necessary. What we need is just a calibrated camera. So that we have a calibration device or a calibration part that is seen on the right, and we basically fit the rendering, the BRDF model parameters that are used always in the rendering to fit the rendering perfectly to the real picture. And this is, for example, some BRDF models have just 1, 2, 3 parameters. It's much easier and faster than if you would use a real measurement device of the BRDF.
And Philip, what cost function do you use? It's an image difference metric.
So this is something that we are working on now. It's basically, first of all, everything has to be very well aligned, right? So that's the reason why we use this VisualLib from the other departments. So we align the measurements, or the picture of the object, and it should be also, of course, an HDR image of the object, because we need, of course, also to capture all the specularities in order to fit the model parameters that describes the specularities to the picture. And then there is a paper from NTNU that we would like to use. They have written a paper on BRDF model mapping, which means it's also together with Karl Gegenfurtner from the Gießen University. He's a well-known vision scientist and color scientist. And the idea is to, in this paper, they have, if you have like two different BRDF models, the question is, can you use, if you fit one model, for example, one model is used by one rendering engine and the other rendering engine uses a different model, how can you compute parameters of a second BRDF model so that the output is similar or close at least to the first BRDF model. And this paper describes quite well how this is done and which kind of cost function are used. And I think what we can do is to, of course, share the reference to the PA companies. And I think it's a much more thorough explanation that I can give to at the moment. But it is, of course, uses image information. It needs also, it has to be, because here there are two, on the paper there are two renderings that are compared, which are perfectly aligned, if you want. And here we have a rendering and a real object. So these alignments will not be 100% perfect, but I think with the vision look hopefully very good. And then there are some different weights for the cost function for specularities. And in our case, we want to make sure that the 45-0 geometry is perfectly matched.
This could be the starting for the optimization instead of random values, couldn't it?
Yeah, it's correct. So we basically first make sure that the 45-0 is correct, and then optimize. I mean, the covariance model, I think it has just one parameter or two parameters. I don't know exactly, but it's just something that should be even with very simple pattern search. And because of the rendering that is quite fast, we could reach it could match in just like a few seconds, I would say. Yeah, I think I mean the whole motivation for this is to allow users of the rendering engine to fit quickly the printing materials or the model parameters to the printing materials without the need of expensive equipment. That's the whole thing. Okay, that's basically.
Yeah. No, it's a cool idea, and since we have I think the ground truth with respect to measurements, the MA98 from X-Rite, the devices from Canon, which measure very, very exact around the cloth angle. So there is some physical-based measurement device available here where we can counter-check, and this is a good approach further. There is a lot of stuff for us, again, specifically in the HDR thing. Where do you set the diffuse white point, and where do you set to reflect what's going up? Because in the renderer there is something like a clipping to 1, but everything above is then lost. So this is something where we need to get some improvements. But this is then more for the two Forschungsstellen, as you see, the FS in our descriptions. These are the involved institutes, In this case, it's IGT in Fraunhofer and Fogra. And for the afternoon, we have a third research institute involved in the project. So that is something where we have also meetings for the involved research institutes. And this is something for our agenda, Philip, to catch up now with the details about this implementation, but not for today. Okay.
No, I'm really curious whether some of the people here who attend this meeting have any questions and maybe suggestions. I think it's important in these kind of meetings also to get feedback from people who would like to use it, because it's one of the motivations. So we have talked, for example, to a very, very big 3D printing service provider, where you can send models for print, and before you print, before you just say, okay, I want to buy this print, you get like a rendering, and this rendering, particularly for color, is pretty bad. And they are very interested in having this included, this rendering engine included into their setup. Of course, people who will send models, they would not have a calibrated display. But if the sRGB values that they are seen on the normal display are already better than what they usually get, then the complaints afterwards are much smaller.
Yeah,
probably it's even the biggest 3D printing service provider in the world or so. So they are very interested in this, and they are going much into 3D color printing now. And the question is somebody here who is also interested in these kind of soft proving, or it's just like a question to the audience.
Yeah, it's like you need an icebreaker typically, that someone is asking a question, then you get 30 follow-ups, but no one is volunteering to do the icebreaker here. We have 26 attendees, so it's quite a good attendance, but still, this is the normal scenario. So I'm not surprised.
Maybe. Oh, okay. Maybe if somebody has problems to understand the concept.
Okay, Tanzima, you can just raise your hand. Okay, just go on, Tanzima.
Yeah, I have a question regarding this to Philip. So right now I'm trying to do the BRDF modeling and include it with ICC Max profiles. So basically with the aim of integrating with color management.
Yes.
So so in the first sentence of this slide, you have said, like, it is written aligned rendering and picture of printed model.
Mm-hmm.
Yeah, so in this, the rendering will basically be in the space of the camera that you're using.
Exactly. So you can see on this half sphere these marks. I mean, it's like a test object. It's just for one material, but you see these marks, the circles, and the idea is really to align this geometrically so that as good as possible. And then you know the light field, and then you know also the environment map, and then you know the angles and then the radiance that is computed by the BRDF model, which at the beginning is definitely the starting point. It will be bad, and then there is an optimization to improve this the match. Yeah.
Okay, so in this case, wouldn't it be limited by the camera and the state of the camera that you're using?
Yeah, I don't think that it's a here limitation, because what we typically do is using a bracket set of exposures, and we combine everything to an HDR image. So what we, of course, there is some, the best thing would be to have like a spectral camera, right? Okay. But usually people don't have spectral cameras, a lot of expensive equipment. But what is possible for sure is if we know which camera it is and we know the we know the spectral sensitivities, we could even simulate the output of the camera using the radiance image. But I think for the moment we just assume that the camera captures sRGB in HDR, which is also somehow not correct, but because sRGB is low dynamic range space, but at least in the linear part, we can do the matching. And yeah, I think at the end it is important that when we have a picture and the picture is acceptable, that our rendering matches the picture, and the picture is typically low dynamic range, which is okay.
Right. And I have another question regarding your constraint. Could you explain a bit more? So is it the measurement of the BRDF that has to match the CIE lab value, or is it the after fitting the model, if at 45.0 the output you will get that has to match CIE values?
So first of all, why we use this constraint? Because we use these measurement devices with the 45.0 geometry, and these are the devices that are used to calibrate and characterize the printing system. And if you would, for example, use whatever kind of diffuse illumination with D8 specular component included or something like that, then we would need to mimic or to extract this information from the BRDF model and make sure that this is similar for the rendering and for the picture. It's basically, we just look into this one angle, in this case 45.0, and we need to ensure that for this angle, the BRDF model and the picture or the color that is extracted from the BRDF model after rendering and the picture match. That's it. It's like a constraint that we want to make sure that the profile is considered correctly.
We have one more question from Yoav. Yoav, you are unmuted.
Yes, please. So I'm Yoav from the Stratasys R&D, and I would like to relate to the question of who would be interested in the technology. And I would like to split the workflow into two programs. The first step is the originating or design program. And this is where the object is viewed on the monitor. And the second step in the workflow is the printer or the driver of the printer, which is definitely in Stratasys code. So the originating software, let's say, for example, Keyshot, should declare their BRDF model, or they should demand parameters for their BRDF models, and the printer provider should provide the BRDF model parameters by some kind of a standard file format for that. And the printer manufacturer can get those parameters as a service from some kind of a laboratory that is specialized in measuring these parameters.
Correct.
That's the comment.
Yeah, I think it's a good comment. That of course, if the materials are provided also by the printer manufacturer, that and of course depends also on how the printing materials are processed by the printer. Because if you process it differently, you are from your systems that, for example, there's gloss mode and this matte mode, depending on how much support is there, if there's support touching the surface and so on, the appearance will definitely change. So that's the reason why it is important to really look into the whole system. But I completely agree. It is important. So this kind of soft proofing could be important to different scenarios. One is in the design process. I think a little bit on about Photoshop, where you can design your picture, your graphics already in a soft-proof simulation, which means you know what you could expect if you use a particular printer. And this could be quite helpful because you can avoid, for example, if the color is not really in the gamut, and you have to choose another one which is in the gamut, and then you have already the tool available. And the other one, of course, is for the quality control by the customer. And for this, and for both, it is important that, or would be very beneficial, if the company, the print manufacturer, material manufacturer, maybe combined, give these kind of parameters to the printing, to the design engine, or to the setup for the customers to control if it's okay or not to print this object. Completely agree.
The challenge is that the design step needs the printing information. The soft proof is only as good as you understand the object you would like to soft proof. And that's why, although you are in the design phase very early, you need to get some understanding of the materials. And so this is also for 2D. Yeah, the 2D soft proof is only good if you have a good printer profile which reflects the actual output on your print later. And the better the printer profile is reflecting the physics and the appearance, the better for the 3D also. And so that's why we need both here, a good understanding of the characteristics and the models for the 3D materials, and having those information chipped by the service provider or the manufacturer, the printer maker, would be nice. But we know and understand that this influenced by many factors. We come to that in the afternoon to see even the post-processing has a huge impact on the appearance, and so also on the BRDF. So even if you print the same, just the way you post-process, you polish the samples afterwards has an impact on some of the visual characteristics, and therefore this is.
But that's
yeah, Philip.
I think that's I think also the reason why. So we work together with the 3D printing who really work a lot on the process, how to get the best output from the printers, and they optimize the post process a lot. So they spend a lot of time to make sure that they have like a workflow where they get the best quality. And this might be maybe something different than the print manufacturer is intended or recommends. Maybe they find a different way to post process, a better way that the print manufacturer thinks is possible. And then it makes really sense to have a 3D soft proof and to quickly adjust the BRDF model also to the post process. Yeah. So they basically would print this half sphere they would post-process in the same way than all the other objects where they are really happy with, and then they would capture it in this viewing booth. I know. Do we have any viewing booth manufacturers here in the PA meeting?
Not in this meeting. They are aware of it, but there's unfortunately no one from Just or GTI.
Nobody here. Okay. Because I mean, I could also imagine that these kind of small viewing booths that we have shown that was built by the other department for scanning. This could be something which would be quite interesting and useful for color communication in the 3D printing field. I mean, it's not a very expensive booth, and if you define basically the boost parameters, you define it's like perfect D50 according to like spectral adjusted D50 illumination in the boost, diffuse illumination, and then if this is if you have a kind of standard boost defined, then you don't need even to measure the environment map all the time, because you could just calibrate the boost by the manufacturer, and then you can give this environment map to everybody who is interested in to buy the boost, and they can then use it for optimizing their BRDF models. So, I mean, this is like a business model, right, for the boost manufacturers.
Absolutely, there are a lot of potentials here, but unfortunately, we can absolutely motivate that to them in a one-to-one information. But so far, right now I think about something like understanding maybe the influence of the post-processing. If there's a close mode or matte mode, and you simply have a slider in your web shop, or everyone that's operating a web shop selling 3D printed products could be interested in that rendering. Yeah. So, and then you just have a slider adjusting for the different output options with respect to post-processing, polishing, and with this slider you translate to the BRDF parameters, and so the soft-proofing design follows. So I have a lot of ideas already, but I think we just right now need to go a step back and fixing the underlying steps to get a very good proof to print match for the basic materials we have, and to make our workflow nice and repeatable and clear. Okay. One option here, of course, is to move the agenda 15 minutes earlier, so we can do the lunch break right now and reconvene 15 minutes earlier. If there's no additional raised hand. Oh, there's one raised hand waiting for name. Who's that?
Oh, hi. This is a question for Marco or for the audience. Just wondering from soft-proofing of view, is there anything on the monitor side that you find that's missing, that you find that it could be beneficial for if there's something the monitor can do it for you for this 3D printing soft-proofing?
Philip, would you like first, or what can a monitor soft?
Oh, I thought it's Marco. I was already talking so much. Should I mean, I think maybe regarding the display, I think, of course, if you have like an HDR display that reflects that where you can get rid of the HDR tone mapping, would be, of course, a very nice solution. I don't know. Probably the Fogra will know better than me. Whether there are color calibrated HDR displays, like from ISO or so, I don't know. I mean, these would of course be pretty cool. I know that there are some displays in the medical area of this for movies. They're super expensive. So we are not talking about thousands. We are talking about 10,000s of euros. But I don't know whether there are also cheaper systems where that are color calibrated and HDR.
Recommendation.
Somebody from Fogra?
Make HDR cheaper. This is the first request.
Well, it depends on how bright it you want. If you need a really bright HDR system, that's going to be very expensive. But if you don't need that bright, then it's possible.
One small thing.
We can talk about that later.
One small thing is, for instance, ISO supports the CS2000 actually as a display device with their color navigator. So when doing the display profiles, typically you rely on the measurement devices out there. But we found that it is better to measure in tele mode, so what the eye sees and not in contact. And so to support a little bit more in that direction with respect to the GUI and also the supported geek laboratory instruments, I admit, but this would be very beneficial to add support for instance, to the CS2000 in your support. We can do it manually, of course, but there would be some, this is a simple request. Philip?
Okay.
Maybe one more thing regarding the display. I could imagine, particularly if we have like glossy prints, that high local content will be important. So you need basically a big difference like of 2 points which are very close to together, because if there are specularities, then there might be like a sharp edge on the screen necessary, and then of course you don't want to have a bleeding of the bright parts into the dark parts. So this could be, for example, an OLED display, but I don't know how good they are in terms of calibration performance. I think if you just use LED backlight, then this might be not good enough, because one LED usually covers a lot of
areas,
and you get like a kind of fuzzy or like a blurring of bright parts into darker parts. But this has to be also investigated in terms of appearance, and if people really care. It's really hard now without having this information to give like a recommendation. So just use an OLED screen or so. Maybe that's not necessary. I don't know.
Okay. Thank you.
You're welcome.
Okay. Then, ladies and gentlemen, if there's no follow-up question anymore, again, this is highly both projects are highly related. So if there's a soft proofing question later on, of course you can catch up then. But then I would recommend to now have lunch break, and then we reconvene 10 minutes earlier than in the agenda. So thanks for your attendance, and talk to you later. We now start the recording back. I forgot it, so sorry. So we are now back on track with our second part of our PA meeting here. And with this being said, we have our right side here, and then we can also ask for our Mimaki, Stratasys, Multijet Fusion printers from HP. Do we have access to the voxel data? Yes, no, binary question. And if there's no, we are here in this third level. We call it currently sealed by K only approach. We have to get more information about it. And then if you have access to the voxel level, you can still ask, okay, they're using inkjet heads. And inkjet heads are either binary heads, so per position, per voxel, you can put drop there of one material, or you have multi-level heads. That means you can even in one voxel cell put and displace or lay down different colorants to actually fill up one voxel with different colorants. Again, you have a volume to fill. It's not like printing where you can leave it out. Yeah, in the 3D world, you have a volume to fill, and it has to be filled. Yeah, and so we can say here, yes. Then we have full voxel control, and we understand really if we make a bottom-down visualization and computation, we exactly know the basic characteristics and can then bottom-up model and visualize the way of the photons. Whereas if you're on the right-hand side here, you just go from a phenomenological approach, top-down, and see what can we measure and what can we model without understanding the underlying physics. And this is what we call here full voxel control, or here at least partial voxel control, if we have this information only in a yes-no sense. So we have voxel data, we can access every voxel, we know every voxel how it is filled, so is it just fine, but then we don't know exactly the perfect control. And this is in the same thing being said in a different way. So you have your 3D data here, you have an RGB encoding of your OBJ, for instance, or verbal or whatever object. You do your print, you do a potential post-processing, and you're all set. This is what we call black box. The next level is already you have a 3D object. You have your, for instance, sRGB encoding or RGB encoding plus an alpha channel, which is honored. You print, and you get your remaining resulting print. The next one, you have your alpha channel, you have your RGB encoding, but you have an access to the CM/K data, and you can actually create a CM/K profile or a CM/K cyan, a CM/K clear white profile, a 6-channel profile to characterize the material interaction. Here in this case, you have to make an RGB output profile. So you have an RGB-based target, you print it out, you measure it, and you label it. This is simply as that. And the next two things here is you have your control, you have your voxel data where you have your voxel information, you know what colorant is should be displayed, but you don't know if there's additional multi-label screening, what goes actually up in those cells. And this is the high level, the full control to fully understand and see what's going on to be able. And this is important for our project because when we would like to model something, it is very important to understand at which point in those pipelines we have actually access and can understand how maybe different voxel locations or displacements actually look like optically in different spatial dimensions or this kind of stuff. So if you don't have access at all to the voxel data, you can't think about this at all. And we don't try to reverse engineer something. Of course, you can do this also, but this is not our idea. So with the 3D printers to the end, you see with this kind of model or idea categories, we have different levels of accessing our pipeline, and depending on this, we can also do certain things with it. So for instance, with the HP printers, we just have an RGB interface, we print it, and full stop, we have to live with it. But this means already that we can try to make an ICC profile. We can still try to think how can we do the profile with a limited set of numbers and patches and not printing out the big expensive ones. Yeah. So still there is some room for doing for us doing something, but with respect to what you hear soon, this is not so powerful. Yeah. The most powerful thing, of course, is to really go down to the high level of understanding or to the detail level of understanding and then model everything bottom up. Yeah, this is a few words about introducing this project, and maybe you can ask us right now if there's something missing or if you would like to hear something more. Just let me know.
We should extend in 3 and 4 to CM/K clear and not CM/K.
Okay. CM/K. Yeah, I fix it to color and control.
Yes.
Then we have all primaries involved. Good point. Yeah, you ask, please.
I have a question. We have two products or features that we offer. We offer the partial voxel control under the name Voxel Print, and we may perhaps used to offer the full control under the name Print from File. Is there any reason you would recommend us to keep supporting the full control option when we have the partial voxel? What is the user value in having the full control?
This is our way to access our targets and our idea in the project to model the printer behavior with a very limited and reduced set of test patches. If we manage to calibrate the basic behavior of your materials, which requires this voxel control, to have thin slices, to have the control over the pure colorants, then we might be able to come up with a model which just needs much less samples than the thousands of samples we need right now. So the basic idea from our point of view is to be able to model the resulting printing process much more efficiently. Maybe Philip, if you would like to add something, or Marco. You can unmute yourself, Philip. You're supposed to.
I know. I mean, the thing is that in order to get a better understanding of what's really happening in terms of physics, the better information or the more information you have from the printing process, the better, because then you know exactly at which position which material is positioned, and you can even infer how materials are mixing and all these kind of things. So I believe it is from this point of view very interesting to get as much information and much control as possible. But I think at the end, it's just like a business decision, right? What kind of information you want to offer, or what kind of access you want to offer to the printers, and what can a customer potentially do wrong if having too much access to the printer. I think in terms of knowledge and in terms of quality and exploiting the full potential of a printing system, then having access to the highest level is definitely.
Okay, let's assume that.
Go on.
Let's assume that a voxel is approximately the size of a drop. So in the partial control, you control what drop is placed in each voxel. And in the full control, you can put 2 drops in the same voxel, and you basically perhaps losing material. So I really don't understand the utility of the full control. I don't think there is any damage you can do to the machine in a full control that you cannot do in the partial control.
This is our first, or maybe Philip, if you want.
Yeah. I mean, theoretically, I mean, it really depends on also the safety situations or the safety protection means that are somehow included into the machine, because theoretically you could, of course, overfill voxels, you could damage the roller, you can do whatever. There's a lot of potential problems that you could create if you have too much control. So basically the print job can break, there's a lot of things that you could theoretically do wrong. On the other hand, if you can have like a subvoxel access, you can print multiple droplets, then the whole resolution becomes higher, right? So you don't have any more 0, 1, but you have more, the bit depth basically increases locally. And then that's of course a good thing to, if you have access to this. Yeah, it's always like two sides of the same coin, right? So you have, if you have too much access, you can destroy things. You can destroy the printer if there are no protection measures, protection mechanisms included into the system. And if you have not enough control, you can probably not exploit what the printer can do.
Okay, so at the moment, the released current product, the voxel print, is the partial control. But for the purpose of these projects, if you want to print a model in full control and you're missing the feature in your printers, it is something that we still support in the laboratory. So if there is any experiment that needs to be done in full control, we can do it.
Okay, perfect. Perfect. That's really cool. It's just tough from the experience in 2D. If you have multi-level screening, the binary doesn't help you. You know, you have light, cyan, and magenta. And if you print your test charts with just the large drop in magenta and characterize it, and then you have maybe 50% of magenta, and you expect your model is 50% of your solid, but actually physically you take another drop size. So there's another drop flying to the paper or to the voxel, then of course you do something better. So the model can be better if it understands the underlying physics better, of course. And in this case, this is just category from our point of view to see when we do the models and we get the feedback from ILM soon, then if there's a mismatch maybe in a specific situation, we can also trace that back in the root cause finding, you know. Then maybe we don't ask, oh, this is the problem in our model. If we know, oh, that could be that here actually a small drop of cyan and not a large drop of cyan would place. So this is really, but a little bit speculation right now. You are good to have the information, but let's follow up with the other presentations to see what we need and specific the underlying characteristic or the fundamental optical characteristic. This is the primary focus of our ILM partner, and this is a lot of depends on what they now find based on the print samples which we have recently created. But I would like to give the mic back to Marco, and then to follow up on our agenda with the proposed agenda, and then we have a lot of time to catch up here with this.
Yes.
Marco ist dann noch der Organisator.
And thank you for your presentation. And now we have a presentation from Ulm. And I think, who is the presenter? Mr. Kienle? Can I unmute you?
Du bist aber in der Kamera gleich, ne? Die Kamera ist an. Du siehst da oben, was die sehen. Nicht so schlimm, du musst nur wissen, dass du siehst.
Yes, so I will present it, yes.
Okay.
Go on.
Okay, so I hope you can see my screen now. Is it visible?
You can see my thumbs up. In the left hand, you can see what we see. So this is a double check for you.
Okay, like this. But maybe we have to go like this. So, okay, so I start. So my name is Alvin Kienle. I'm head of the department Quantitative Imaging and Sensors. and today I will talk about physics-based rendering. So this is our institute. So we are part of the Innovationsallianz Baden-Württemberg, which functions like a Fraunhofer Institute. So this is the outline of my talk. I first will give you a small overview about light propagation in scattering translucent media. Then I will talk about the determination of the optical scattering and absorption properties. And finally, I will connect these both to show some physics-based rendering results that we work on since about 2 years. So this is a principal scheme. So if there is light incident onto a scattering media, then a small part is reflected on the surface. So if the surface is plane, then you have a specular reflection. If it's rough, then you have a diffuse reflection. We talked about this today already. And then, but the most of the light is going into is going into the scattering medium, and then in the scattering medium, it's scattered and absorbed mainly. Of course, there can be some fluorescence. Typically after many scattering interactions, part of the light is reflected or transmitted, and part of the light is absorbed. So this is the principal scheme, and the exact solution within classical physics is solving the Maxwell equations. So we implemented several methods. We derived our own method to solve Maxwell equations. Here you have to know the refractive index, the complex one, with a high resolution. Therefore, you can do these simulations only for small volumes. For example, to characterize single scattering. This means for doing simulations for larger volumes, so we have to make an approximation, and this is the transport theory. And this we solve with Monte Carlo simulations numerically or analytically. We derived solutions for a couple of interesting geometries like layered geometries. And here you have scattering coefficient, absorption coefficient, scattering function, which gives you the probability for scattering in certain directions, and an average refractive index. And then there's also an approximation of transport theory, diffusion theory, but we will not deal with this. So the results I will show are mainly due to the Monte Carlo simulations for the rest of this talk. I just mentioned that the scattering coefficient and the scattering function can be combined to an effective scattering coefficient. So when we do measurements, we measure the scattering and the absorption properties of materials. Often only the absorption and this effective scattering coefficient is determined. Okay, I show one picture concerning the Maxwell equation. So this is a solution of a plane wave incident onto a scattering medium. Can you see these movies?
Yes, perfectly.
Okay, thank you. You see then the light propagation in this area, and with all the all the interference effects due to the solution of the Maxwell equations. And you can also compare then, for example, the intensity versus depth with solution of transport theory. This is here given for 3 different thicknesses. And then you can test if this approximation of the transport theory is valid for the considered geometrical properties or particles, for example, in this scattering medium you are looking at. Okay, then for solving the transport equation, I already said that we use, for example, Monte Carlo simulations. Here, probably know the scattering probability and the absorption probability is used together with the random number generator to calculate the path of the photons. Then the considered or wished parameters like the absorption position or the position of reflected light is stored, and after many photons, finally you get in the limit of a huge number of photons an exact solution of transport theory. So we now have Monte Carlo simulations in principle for arbitrary surfaces. We can include special effects. We can calculate polarized light. It's GPU accelerated. We can also calculate anisotropic light propagation, which means that if there is a certain structure, like in the tooth here in the dentin, which is aligned in a certain direction, or like fibers in the muscle, this can also be considered, because this changes the light propagation strongly. And when we compare then Monte Carlo simulations to our analytical solutions, which we also found, we can see that they match if you use a huge number of photons. So these are both, so two different situations with different incident diameter of the beam. Then you see that they match very well. There's no difference. But if you plot here the relative difference, then you can see only the statistical errors due to the Monte Carlo simulations. Okay, this is what I wanted to say to the first part, is how we treat the light propagation in the scattering medium. And now the second part, we look here to the point where we determine the optical properties of different media. So we developed a variety of different apparatuses to measure the optical properties. I just show 3 of them with 1 or 2 slides. This is spatially resolved reflectance with camera-based equipment, integrating sphere measurements, and using spatial frequency domain imaging. And all these measurements, they are validated by phantoms. So we create these phantoms by ourselves. These are based, at least this one here, are based on epoxy resin, and we add scatterers and absorbers, and to get phantoms where we exactly know the optical properties. And also here we can create 3-dimensional shapes. So one method we use is we measure, if we have a slice of a scattering medium, the totally transmitted and totally reflected light. So my coworker Simeon Geiger will talk about this just later, so I will let this to him. And when we compare these measurements to the calculations based on transport theory, we can get the absorption and this effective scattering. So this is one example. So this is, we take water here in this validation test, nanoparticles as a scatterer, trypan blue as an absorber. So it's a heavily scattering media, and with here no absorber in different concentrations of trypan blue. And then if we compare this absorption coefficient, which we get in this highly scattering media using our theories, then we can get the absorption coefficient as if it has not been in the scattering medium. So you see, this is the collimated transmission is measured without scattering, and the absorption coefficient and these measurements in the scattering media divided by the concentration. Here we get here in principle the same absorption coefficient. So and this is the absorption, and then if you want to have this effective scattering, which is needed for the simulations, then you can also get this spectra here, and these are the measurements of these different concentrations of trypan blue. You see that in principle there's no influence here by the absorption as expected. And so the second device is, so here we need, for the first one, we need slices. If we don't have slices, we can use this device. We illuminate the sample at a certain point and measure then the intensity versus the distance to the incident point. So here the light is incident, it's scattered, and then it's reflected, and this plane is just imaged onto a camera, and then you get this spatially resolved reflectance, so the intensity versus angle, which is shown here. So here is the incident point. You have the highest intensity, then the intensity is decreasing versus distance here. And we do the measurements in this setup at different wavelengths just by changing the incident wavelength. So you see here 3 different wavelengths. You get for each this decrease of the reflected light versus distance. Then we compare it again to our solutions of transport theory, and therefore we get again, similar as before, here the absorption spectrum of our samples. We again added in this case, so we used here interlipid, which is a emulsion similar as milk, and we added here ink with different concentrations, and you see in principle the absorption of ink, and here the absorption of water. And the final device I want to show is modulated imaging or structured light illumination. You can also call it fringe projection. Here, patterns are projected to the scattering medium, and then with this device here, and then we use a camera to look at the changes of these fringes due to the scattering and due to the absorption. And when you measure these changes, so the amplitude and the shift of this pattern, then you can get now at each position absorption and effective scattering coefficients. This can be seen here, for example. So this is a measurement on a hand, and then you see here the absorption now spatially dependent. So you in principle can get at each position here the absorption. But you can also get, for example, as is well known, using the string projection, the 3D geometry of your sample. So this is an apple. So we measure the 3D shape of apple and simultaneously the absorption coefficient. And then you see here higher absorption, and when you cannot see it with your eyes in this case, but if you peel the apple and put if the skin is taken away, then you see that there's an internal browning at this position. Okay, sorry. So this is the third method. So in summary, this means we have different possibility to measure the absorption and scattering properties, and we have different possibility to do simulations of the light propagation. And now, since about, as I said, 2 years, we put them together to do rendering. Rendering or physics-based rendering. And here, for example, we rendered a vein and an artery. We changed the depth and the diameter of the vessels. And you see then, because blood, of course, has a red color, reddish color, but if the blood is within a vessel, which is in the tissue, then the color changes. So if it's superficial, then it's and small, has a small diameter, then it's looking reddish. If it's still superficial, but you increase the diameter of the vessel, then it looks dark bluish, like under the tongue. And if you have a relatively large depth and large diameter, then it's looking bluish. And similar for artery, but here it's more difficult to get a bluish color. So this is one example. Other example is here. So these are epoxy resin phantoms we made. So we know the optical properties, absorption and scattering behavior. And here this is a lower scattering parallel epipede, and this higher scattering one. And these are photos, so the images. These are images, real images here. And now we took the whole scene. So we illuminated them from this side in the simulations using the spectral behavior we measured before and the incident angles. And then we did the calculations using the Monte Carlo method. And you see then here the shadow, and then the light goes in here, and then it's scattered typically 100 or even 1,000 times. And then we measure only or detect only the light which is transmitted here and is falling into the camera. The camera is approximately where you are looking at, where your eyes are at the moment. And we only look at these photons and produce then a picture due to calculations between 400 and 700 nanometer at about, in this case, 31 different wavelengths. You see that there's almost all effects are included, and it's very difficult to see a difference. Most difference is due now to the fact that that here we calculate we did not consider the fact that for the real images we have errors in the imaging setup in the lenses. So this was not considered, and also the angles here are not exactly the same as here. The positioning angle of the cuboids are not the same. Then we can also create some movies. So just in this case, we turn it together with the incident source and can then simulate the cuboid in this case. So one application is in the dental medicine. Here you see images of some restoration materials, and here the simulations. So we measure the optical properties here of these materials. Here we simulated them, and we see here is the difference. It's almost not possible to see any difference between the simulation and the imaging. And finally, here we have a tooth. So this tooth consists of different materials, and we measured again the different materials, and then we simulated this tooth here, and it looks very, very close to the real one. I think almost it's not discriminatable. Here, and one important step is here, the calculation time. So when I talk to my colleagues at the University of Ulm in the informatics department, they say if they use their programs, they would need for the whole simulation several years. And now this simulation we did in the whole video in 4 hours, but in the last 2 weeks we succeeded to do it in 4 minutes. So it's about a 4-second video. So it's just about a factor of 60 to do real online rendering. And this has to be done with one GPU. Of course, we could use more GPUs, then we are very close to real time rendering. So in conclusion, so we determine the optical properties and also the geometrical properties, scattering, the absorption, the scattering function, and the refractive index. In our department, we also can measure the three-dimensional geometry. So this is a device we just today delivered to the University Hospital to Tübingen, where we use this string projection. So this is made by ourselves here for measuring, detecting melanoma. So here we also need the 3D profile of the melanoma and also the content of water, of eumelanin, pheomelanin, of hemoglobin, which can be done with this device within 2 seconds. So the measurements can now be done at 8 or 9 wavelengths in about 2 seconds. And this can also be used for getting, of course, the results needed to do rendering of these objects. Here, of course, it has also to be considered the surface roughness. You did some simulation, just changing the roughness here in that area. And as we all know, this has a huge influence to the appearance of the phantom or of the object. Okay, so in summary, the two basic things we have done in the last 2 decades, I would say, measuring the optical properties and doing fast simulations can be well connected to do physics-based rendering. And I want to thank my colleagues and you for your attendance.
Yes, thank you for your presentation. And are there any questions from the participants, attendees?
Yes. I would like to ask, what approach did you use to model roughness? Again, we can also use the mic, but there was one question from Alina.
Yeah, so we also, this is one thing we began in the last month. So we have a combination of this Cook Torrance model and more microscopical model. So we are just trying to include these models for our simulations, and we want to measure these together with the volume scattering using, for example, this string projection apparatus. Because we did already some measurements, and we see that if we do them, we can also fit the reflection or the reflection from the surface and to a certain model and to get the roughness parameters.
Yes, okay. She said thank you. Yeah, I translate here as possible. No problems again. Yeah, very impressed.
May I ask also one question? Sure. So yeah, I think it's a very interesting technology that you have developed, and the comparison, particularly between the real and the simulation, are really great. So this is impressive. I wonder, like, if you compare both, and for the rendering, you of course also need to measure the light distribution, the incident light. Can you maybe give us some information about what you do to measure this? For example, on slide 15, right? So you have, is it like a very simple point light source that you just place at the same position? And but then, of course, a point light source, if you have like real light, then you have a distinct distribution of the light. Or are you really measuring some light at the point where the object is placed using, for example, the like mirror ball, how it is shown in the 3D softproofing?
Yeah. So we have two different light boxes. So one was just, the first one we used was a very simple one. We just made a box with an opening and used the sunlight, which is coming into the window, and measured this. And then the next step was, which we made maybe 2 or 3 months ago, where we used, I think, a white light LED and use a diffuser and illuminate it, and then to measure the angular resolved reflected light and use it as an input. And the spectral behavior we measure together with the camera using a sample where we know the reflected light versus wavelength.
Okay.
So maybe we can see pictures the next time to get a better understanding. And there's a question from Ali Payami about the 4 minutes rendering time. What was the concrete rendering hardware configuration? Is it based on GPU or CPU? Just the rendering hardware configuration details.
Yeah, so this was a normal PC having one GPU card. So state-of-the-art personal computer.
It's like my boss used to say, work smarter, not harder. Yeah. Okay, thanks.
I have maybe one also related question to this video. So there are, for this video of the tools, this is 4 seconds long, so which means approximately 100 frames, right?
Yeah, I think so, 200 frames or something like this.
200 frames. Okay.
Yeah.
Okay, it's 100. Wow, that's so. This means like for one still picture. What is the resolution of the video?
We made calculations about 1,000 by 1,000 pixels. So
okay.
We would have 1 million pixels approximately.
So this means that like for still images, this is basically, yeah, it's real time. It's not like that you need to wait really. It's like, I don't know how many is it's like 2 seconds, right? Less than 2 seconds.
Yeah, in principle, yes. So of course, if you say we use 31 wavelengths and so it would be even less. But we made a lot of variance reduction methods, but there's in principle no approximation. So it's still an exact solution of the transport theory. Yeah. And now the problem is that the simulations, they are not, the part of the simulations gets smaller and smaller. So the overhead is now the problem. We have to reduce the calculation time for all the overhead things. So this will be the next point we have to look at.
The tooth is a non-homogeneous medium, or it is homogeneous?
It's not homogeneous. It consists of different materials and different areas where this material is used.
So this means, for example, if we would have like this voxel representation, you could directly use this very fast simulation, which would be really interesting.
Yeah, so we use a lot of voxels. I don't know it by heart, but so about, I would say, maybe many millions, I would say, voxels. But we have only, so in principle, for each voxel, we could change the optical properties. But in this case, we only have a small number of different materials.
Sure.
So we got the 3D shape of all this, of the whole box, of the whole tooth, of course, and also of the different materials implemented in the simulations.
Thank you. Great.
Cool. Looking forward to see this applied for our models and for our materials here. Yeah. Before we continue, I see that we have 2 additional participants here, and I would like to introduce you very briefly. Rui He, can you briefly introduce yourself? For some reasons, I can't unmute you. Satoshi Oyama, please. Okay, sorry, but Shigeti Kato. I see a new name here. Shigeti Kato, can you introduce yourself briefly? Geht nicht grün. Safe muted. Okay, for some reasons I cannot unmute you here. If you try it from your side, please do so. Otherwise, we try to do it in the next break, that anyone gets a chance to introduce themselves. Okay, with that being said, we go back to the agenda, make Marco the presenter, and proceed with our agenda.
Thank you. We are good in the time, and and the next presentation is about cuttlefish, basic presentation about this printing driver. Philip, you make the presentation, or Mustafa? We have one more. Oh, sorry. Then back to the agenda. We have one more presentation. I think we have switched 4.2 and 4.3. So we have now the presentation about from Ulm. And I unmute. Or can you unmute Simeon? Okay.
Hello, here's Simeon Geiger. Can you hear me?
Yes.
Okay, how can I share my screen?
Good question. Ich glaube, das musst du machen.
Ich kann auch nicht, ich will nicht. Steht nicht mit
You go about the web interface of the browser.
Yes.
Yes, I think that it's not possible to make a presentation from this. You can send me the slides, or you log in with the GoToMeeting.
Normal application.
Normal application.
So you started this morning with 2 logins, the web and the other one. So please use the normal, the separate GoToWebinar launcher program, and that launches a small tool which then is able to share your screen. Or you just send us your PDF or PowerPoint screen. Or you maybe.
Yes, I will send you the slides because I don't have access to the Excel.
Okay.
Okay, I sent them just to Marco. He should just receive
perfectly,
them.
and we share his screen. Yeah, perfectly. And maybe in the meantime, if we really eat. Okay. So just to have this nice flower to kill your time for a few seconds. Wait to get the email done. But you can already orally introduce the work, Simeon. Don't wait for the slides. Just start off orally and then show it in a second.
Okay, so I'm working as a researcher at the project, and I will just present the different techniques we use and the results we get when we try to really determine the basic optical properties, not from any materials, but now from real 3D printing materials. And the next step is to use these optical properties in simulations. And I will also present in a short way how this is supposed to work. So I think now we have the slides online, so we can start.
Do you use an analog mic?
So,
sounds like that you are using
I just use my headset microphone.
Okay, go on.
So can we go to the next slide, please? Okay, so as we already heard in the talks before, that the preparation of from 3D printers is expensive, and if you want to use 3D printing, you can't use the same modeling as for 2D printing, and that's why a physical-based simulation is necessary. And if we have a good physical-based simulation of the 3D prints and the light propagation, then of course less test measurements and less patches are needed, which will reduce the cost. So this is the main motivation behind all this project, as we already heard in the previous talks. So when we go to the next slide, I have again a quick overview of the different light propagation theories that are used at our institute, and I will mainly talk about the radiative transfer equation. So on the next slide, it will be highlighted, and you will see that this is like a ray tracing approach, but not on this only on the surface of the material, but also inside. So the light goes inside, and it will be scattered and absorbed, and but all the wave character of the light is neglected. So again, on the slide number 6, can you just move to slide 6? There you can see again the main optical properties we need for the bulk materials that are used in the printing process. So this is the refractive index, the scattering mean free path, or the scattering coefficient, which is a measure how long the light will travel before it changes the direction. Then the absorption mean free path is a measure how long the light will travel before it gets absorbed. And then, of course, at each scattering event, the light changes the direction, and how it changes the direction is described by the scattering phase function or scattering function, which can be approximated by just a single factor, the anisotropy factor. So on slide 7, you will see how we try to measure the refractive index. Therefore, we need prisms that are printed out of the material that is used in the 3D printing process. And then we just shine light on the prism and measure with a CCD camera the different angles in which the light is refracted. And from this, we get really a spectrally resolved refractive index of the material. So we get the dispersion relation of the refractive index. And we validated this process, which you can see on slide 8. So here is the measurement with our setup, and then the literature value for 2 different classes. And you see that they match very well. So we use the same setup to also measure the samples from the 3D printers. On slide 9, you see a sample from a 3D printer for the transparent material. This is easiest to measure because all different wavelengths just go through. And but you see that the refractive index in the visible light range is not the same, but it changes with the wavelengths. Okay, so this is about the refractive index, but we have more optical properties, namely the scattering and the absorption coefficients. And these are measured with the integrating sphere setup, which you can see on slide 10. So there's the probe port, and there a very thin slice of the material is placed, and then we can shine light from the right or from the left. So you have, as you can see here in the image, we have 2 light sources, and if we shine light from the right, we measure the transmittance, so what goes through the medium, and if we shine light from the left, we measure the light that is reflected from the medium, so we measure the reflectance. And with these 2 measurements, we can extract 2 parameters, and this is the reduced scattering coefficient and the absorption coefficient. And we also do this for the whole wavelengths. That's why we have also spectrometers connected to the integrating sphere setup. So on the next slide, you see a measurement we did. And you can see that for this sample of the white material, the scattering coefficient changes with the wavelengths, and the absorption coefficient also changes, but not so much. But if we go to the next slide, we have the cyan material, and you see a big increase in the absorption coefficients in the red area, and that's why if the red light is absorbed, then of course the material itself looks more blue, and that's what we have here with the cyan material. So when we measure these, we can then later take these values we measured in our simulation for the physical based rendering, but we really need to characterize our materials first. That's why we do all these measurements. So on the next slide, 13, I give a quick overview for other methods to measure these optical properties. As Mr. Kienle already said, we have also the spatially resolved reflectance, where you measure at the surface. We have the collimated transmission, where you only measure the transmission. And we also have the spatial frequency domain, where you shine in like spatially varying patterns, like sine patterns, and then you also can extract from images the scattering and absorption coefficients. But it really depends on how your materials are sampled. So if you have thin slices, then the measurement with the integrating sphere is very good. If you have thick slices, then you can also use the spatially resolved reflectance or the spatial frequency domain. So it really depends on your materials. So on the next slide, we will have the solution of the radiative transfer equation. So the Monte Carlo simulation, it's a numerical stochastic method. It has stochastic noise, but you have, in principle, can calculate it with arbitrary geometries, and that's very important for the 3D printing. That's why we use this approach here. And the spherical harmonic approximation, it's also a solution to the radiative transfer equation. It's has no stochastic noise, but sometimes you have to use very high orders to get good accuracy. And the solution we only have for some geometries, for example, for layered materials that are, or for infinite materials, but not for arbitrary geometries. So on slide 16, you see a very simple simulation I did. So it is a slab model with a regular voxel grid, and in each voxel can have different materials with different optical properties like refractive index and scattering coefficient and so on. And then we illuminate it from the top, and we can detect at the top and at the bottom, so we can detect the transmittance and the reflectance within a specific radius. So on the next slide, you see just a very basic sample I did, where I just put voxels with different materials side by side. So this is just a pattern that mixes two different materials, and you see the properties of the materials on the bottom. So the mu s prime and the mu a and the anisotropy factor and the refractive index. And here they only differ in the scattering coefficient mu s prime, as you can see here. And then I just simulated how much light would go through this slab and how much light will be reflected from the slab. And this is shown on the next slide. So I changed the voxel size. It is the x-axis. It's logarithmically, and if you have very, very, very small slices, then it's like a homogeneous medium with the scattering coefficients just be the mean of the two scattering coefficients, because if you have very, very small voxels, you could just mix the materials. But if you have larger voxel sizes, then the reflectance and the transmittance, they go away from the green line. So then the light that comes back or go through is not the same as if you would just mix the materials. So it really depends on the voxel size, and you see for a voxel size of 0.04 millimeters, for example, this medium would appear 1.4% darker than if you would have just mixed the materials with very small voxels. And on the next slide, the same thing is done, but with constant voxel size in the Z direction. So only X and Y are getting smaller and smaller. And here you can see that the results are different. So this time for large voxel sizes, the reflectance approaches the mean of the reflectance of the homogeneous layers. Okay, so this is not the reflectance if you just mix the materials, but this is like if you have a thin layer of just one material and a thin layer of just another material, and you measure both times the reflectance, so how much light comes back, and then you take the mean of this. And this is different from the green line where you just mix the materials and then make a homogeneous layer of the mixed material. So these simulations already show that it's really important for the 3D printing process that if we want to have exact simulations, we have to know how the distribution of the voxels and the materials in the voxels and the sizes of the voxels are, because only then we can make accurate simulations. And on the next slide, you can see what this could be used for. This is another image of some rendering where we know the optical properties and we know the distribution of the optical properties, and then you can really calculate the color impressions. So the left is the camera picture and the right is the rendered image, and it's really looking very similar. So the last slide is the summary. So for the 3D printing process, of course, we have to characterize the base materials. We have to know the spectrally resolved optical properties. And if we know also the distribution within the object, then the color impression can be calculated in transmission. The next part we also have to, we will investigate in more detail is what about we have boundaries between different colors. Do we always need to simulate the full object, or is it also possible that we can do some simplifications here? And of course the influence of the surface and the surface treatment, because the manufacturers, they treat the surfaces of the objects differently, then it has a big influence, and this will also be investigated in this project. Okay, so thank you for your attention.
Thank you for your talk. Are there any questions?
Yeah, we have Joab asking. Joab, please. Can you unmute yourself, Joab?
Okay. Yeah, a question. Can I predict from this study that if I change the half-toning or dithering methods in the model, let's say from white noise to blue noise, then it will change the optical appearance characteristics of the model?
Okay, I don't know exactly what the difference between your noises is in the half-toning, but in principle, if the voxels are not very small, so if they are very small, then there would be no difference. But if they are not very small, then of course the distributions of the voxels within the printed object, it changes the appearance. Yes.
Thank you very much.
Yeah, that is what we would like to predict, getting the voxel access and then predict the appearance. And for instance, having those functionality, we could optimize the half-toning. Yeah, you don't have to print it every time. If this works, you can use this kind of preview for optimization your half-toning. So this is not only for print service providers interesting, but also for printer maker. So yeah, very cool technology, and we are really looking forward. Unfortunately, we are a little bit late in the making of 3D prints for some reasons. So that's why ILM was not able to show intermediate findings on our printed samples. You know, the prisms I've shown before, they are not older than 1 week, to be honest. So that's why they don't have access to it. And so we expect the next time, hopefully the same accuracy, just with our samples. Okay. If there's no question, we can.
I have a question to Mr. Geiger. He sent you this samples for Newell Packard. Is this possible to measure these samples with an under measuring device or geometry to get the refractive index and the scattering index and so on, or it's just not so easy?
I think with the Hewlett Packard, it's really difficult because there's no apparent translucent, so it looks really very opaque, and then the refractive index is very difficult to measure. And the optical properties, we have some methods also to measure the optical properties for very opaque material, but this is I think it's also not so easy.
Okay. Okay, thank you.
Okay, Philip, you can ask the question and then already start the presentation with the cuttlefish. Again, can you unmute yourself? Yeah, please. Okay, we make you presenter now.
Okay.
Hier geht's natürlich. Okay, go on. We don't hear you. Let us check. It's muted. You are muted, Philip. Now it's going on.
Okay.
Go on.
Now you can.
Just one moment. We record this session, Philip. You are not at the beginning. We say
it's fine. This is
okay.
Yeah, this is fine.
Okay.
No problem.
Okay.
Okay. So yeah, I was asked to present some of our 3D printer driver cuttlefish, and yeah, basically what we do is what does a printer driver do is to get as an input, particularly for 3D color printing and appearance printing. It takes as an input the shape and the visual appearance attributes like color, translucency, gloss, and maybe even material properties if you want to print soft and hard materials. And then it basically computes the material arrangement in the printing system and adjusts the print process parameters so that these appearance attributes are reproduced as good as possible. And cuttlefish is such a printer driver, and we use kind of linear workflow which consists of multiple components. So we have a kind of pre-processing component, a voxelization component. We have a component that computes distances in the object. Then we have a perceptual component, a half-toning component, and also a component that connects to the printer, to the firmware of the printer. And the pre-processing component, what we do is because the materials, not every material, but many materials, particularly in protein jetting, are translucent, so there's an internal blurring effect. what we do is we adjust the level of texture detail to correct this blurring effect. And then, of course, what we also do is we orient the object into the build tray so that it minimizes, for example, the printing time. So here, for example, you can see this blurring effect. This is a print without this texture enhancement. It's a little bit more than a texture enhancement, but basically a texture enhancement that we added here in the pre-processing step. This is without and this is with, and you see that here the blurring effect just blurs out these fine texture, and here you can see much more details. Then we have the voxelization component, and here, of course, not all printing objects are watertight and have maybe also some other errors. And what we do is we have a very robust way to voxelize objects. So here, for example, you see a lot of holes, and then after voxelization, these holes are gone. This is not done in. This is already done in the voxel resolution, and it's not done in the mesh that goes in. Then we compute distances within the object, and this is important because if you have, for example, this object here and you slice the object at this position, then the color signal and maybe also the translucency signal is just given on the surface. And you see, this is basically a slice through this object. And what we need to do is to transfer this information on the from the surface to the inner part of the object. And what we do here is we compute for each voxel, and these could be many billions, dozens or even hundreds of billions of voxels. We compute the shortest distance from each voxel to the surface. And then we transfer the color that is on the surface, or the appearance information of the surface, to this voxel. It's of course possible that there are more than one voxel on the surface that is closest to the inner voxel, and we just take one of these arbitrarily. And in the pre-processing, in the perceptual processing step, we use somehow ICC profiles, but typically also enhanced profiles that also deal with translucencies. And the idea is to compute material ratios at each single position of the object that reproduce the overall appearance of the input appearance. So for all the characterizations of the printing system will basically be placed and used in this component. And finally, because the printing systems can hold one material per voxel or even multiple materials, but a small number of materials per voxel, what we have developed is also a blue noise half-toning system that avoids any agglomeration or unnecessary agglomeration of materials that might be visually disturbing. And the last step is slices are sent to the printer.
Philip?
Here's an example. Here is the anatomy model, and what you see here that looks like an MRI. They are basically slices of this model, and you see that part of it is transparent. So we need really the information and fill all the materials, and all the materials in this part here have some influence on the overall appearance.
Philip?
After printing, so you can, yeah?
If you go back to the pipeline, at which step exactly you do the separation? In which step you work on the CM/K clear white domain and not in the RGB alpha domain anymore?
Yeah, this is basically done here. So we compute material ratios from the signal. So here we have the signal can be, for example, whatever kind of RGB, so color or alpha. And here we compute the material ratios.
Okay, this is okay. Okay.
But material ratios means that for each voxel has, for example, cyan, magenta, yellow, black, and white and clear material.
This is both gamut mapping and separation. Because we normally,
yes, this one, yes, correct.
In our world, the 2D world, we typically separate between gamut mapping and separation, just for the sake of understanding. But of course, it is then part of the same table. But this means both gamut mapping and separation.
Yeah.
Okay. Good. Thanks.
Correct. Correct. The gamut mapping. Yeah, we build similar to the regular ICT profiles. We build these multi-dimensional lookup tables, and they contain separation, but also the gamut mapping in one table. But of course, there's because we are dealing with appearance, so it's not only color. We have also gamut mapping for translucency, and in future also for gloss. And this is done here.
Yeah.
Okay.
One more question from my side to the slide, the last slide. This interface to the printer. This is another software. This is not Cuttlefish. This is the GrabCAD voxel engine, or how it's called, for the Stratasys printer. Is this correct? Or?
Yeah. So the interface to the printer means that every printer expects different data, and this means that this component has to be adjusted to every printer. So, for example, the GrabCAD voxel print, it uses PNG files with a distinct type of PNGs and slice data, and it can also use bitmap files. And so the pipeline, if we adjust this pipeline, for example, to the Stratasys printer, we need to have a different component here than if we, for example, drive Mimaki pipeline or other pipelines.
But
and the data that goes out, excuse me?
Is it the only one possibility, the GrabCAD, or is there another possibility to get use the slices with the Stratasys printer? Is there another?
You mean if there are other ways to drive the printer, or what was the question?
Yes, with the slices. I make the slices with the Cuttlefish, and then the interface to the printer. Is GrabCAD the only one solution, or is there another solution to do this?
Can we voxelize our data and print it elsewhere, where they have no voxel engine license?
For example.
No. Like for the Stratasys printers, you need to have GrabCAD voxel print. That is it's mandatory to use it, because it also computes, for example, the support material. And for the Mimaki printer, they come with for this you don't need this. You can just use it for every Mimaki printer.
Okay, thank you.
So that's a difference. For the Stratasys printer, you need to buy basically the GrabCAD voxel print in order to use it. For the Mimaki printer, it comes with the printer. Okay.
Thanks.
Yeah, and it supports not only polyjetting, it supports also laser melting, DLP, FDM. It's basically many of the components can be reused, so we need to just adjust a few of the components to drive it. And output formats could be bitmap related files, but also G-code or common layer interface for SLM machines. Different file formats, also interesting voxel stacks as an input. For example, in the medical area, it is quite interesting. And it also allows people to write their own plugins, their own components, so and to include this into the Cuttlefish workflow. Here are a few examples. So what we have here are some unique features that we jointly calibrate color translucency. So this is the VEX, for example, model, and this is a reproduction of the VEX model by the printing system, by mixing the materials so that it also, to some extent, replicate the light transport perceptual properties. We optimize the level of detail. This is kind of important if you want to work on these kind of very fine details because of the to correct the blurring effect, and then of course this robust voxelization. So for example, this object here that I showed already. It is an object with a lot of problems because it's a scan, and there's a lot of scans that have these problems. Particularly on this side, there's basically no information what is really in, what is out of the object. And you can put these objects into Cuttlefish, and you get this out. What we also support is that you would typically people say that you have complete design freedom in 3D printing, but that's not completely true. It's possible that if you are close to the print resolution, or at least below the minimal wall thickness, that the printing system is not able to reproduce these small geometric features. And for example, if we have here an anatomical part and these nerves here, with a voxel resolution, these nerves are so thin that they are really not fully connected. This would mean that if you would print this, this part will just definitely not be, they will just be, break in the post-process. And what we have developed is, it's also part of the Cuttlefish pipeline. We do an adaptive thickening, which means just the too thin parts are thickened. And if you look at, compare this, so these parts, for example, are not thickened, but just these parts are thickened. And you can also print this. You can do the thickening with clear material or with normal material taken from the closest voxel. So you can create very, very fine structures. I think the whole, probably this one here would be maybe a centimeter or so. Okay, where it is used, for example, in Hollywood, we Cuttlefish printed 106,000 objects, like basically the faces of the stop motion animation movie from Leica. But also some awards. And this is something which is quite interesting, and we are working now on it. It's ocular prosthetics. And here, it's a totally handcrafted business at the moment. A lot of people actually in the world needs ocular prosthetics. They're quite expensive. Takes a long time to get one. Usually patients need more than one in their lifetime. There are some known people who had also ocular prosthetics. And today, this is, for example, the German way to do it. It's a glass eye. I think in Great Britain and in the US, typically they use resins for this. And the ocularists basically paint this. And yeah, you can basically create this appearance using 3D printing already. And it costs like less than $5. And we are now working on a complete workflow from medical data, like optical coherence tomography data and color calibrated images of the healthy eye. We recreate the prosthetic eye and use cuttlefish to print the fine small details. And so it just takes, instead of multiple weeks, it takes probably from the scanning, it's a completely non-invasive way to capture the information, to the final eye. It just takes a few days. I mean, the printing process probably just takes a few hours, but packaging and all this and polishing, this does not come out like this out of the printer. It needs to be polished. It takes probably 2-3 days to get the prosthetic item. Yeah, and then there are, of course, commercial heritage. These are scanned objects by our 3D scanning department. These are the prints by cuttlefish. Yeah.
One stupid question about
Sure.
and special ink, or not the inks from the Stratasys, or have special inks for this print these eyes. Or
I can barely hear you. Can you?
Do you use the normal?
Can you repeat the question?
Do you use the normal inks coming from Stratasys, or are these special colorants?
Oh. That's a good question. So actually, we tried one material called MET16, which is completely transparent and biocompatible. And so this here, for example, is printed with the normal inks. There are now tests going on that investigate how far away the other materials are from the MET16. So it's not. So we are not doing the testing. There was done at some laboratories in UK, and at the moment, what is possible already is to print the whole thing is embedded into like a transparent shell, which can be MET16, and the internal part is a normal Stratasys material. And and then the question is, how much is the leakage between the normal Stratasys material and the outside, and whether it is a problem at all, because it might be that the normal Stratasys material is also biocompatible, but it is at the moment not certified to be biocompatible.
Yes. Okay.
And but this is something that I would say is a critical thing to get this prosthetics accepted. But because there's this MET16 material, we are pretty sure that there will be just a few tests necessary to show that if this shell here is thick enough and does not create any visual artifacts, that this is safe for the patient to take this eye. And even so, the inner parts of the eye has not the same biocompatibility level than the outer shell. But this is basically printed with enormous Stratasys materials.
Okay, thank you.
Cool.
Okay. This is quite interesting because this is basically the next step, the volumetric step. So this is a guy from Autodesk, the vice president. And so what I showed you before is mostly that the input are meshes, right, with some textures on top. But there are already tools on the way, for example, from Autodesk, that have a complete volumetric design. So you can basically design completely in voxel. And we can take the same way of mixing materials to print these kind of things here. I mean, this is, of course,
We don't hear you.
Okay. No, it's just okay. There's some noise from some audio from this video, but probably you cannot hear this. No, it's what will be one of the next things is to also completely support the volumetric input, and this is and to transfer the volumetric input as good as possible to the printing system. And I just want to mention one very interesting thing, because what we talk at the moment with these graphical 3D printing so far, except the multi-jet fusion, but particularly with polyjetting, are not really made for withhold some mechanical stress, and they're not so mechanical durable. So you can print prosthetic eyes, but if you want to print something that you put into a machine or have some mechanical force attached to it some moment, then these parts will typically break. There is a few very interesting technologies now out, and particularly new print heads that can print high viscose materials. So I think that this polyjetting will move from a normal, typical prototyping technology to a technology that can also create real-world parts that you can use, eyeglass frames, for example. And the design freedom of polyjetting is so gigantic, because you can use transparencies, you can adjust the gloss level, you can do color, full color. That I think it's a very big potential in this technology. Okay, and that's just the outlook.
The volumetric input. Can you elaborate on this briefly? What is a volumetric input different to a texture map with an OBJ file? Just to repeat.
Yeah. Yeah. For example, if you have we have already the capabilities of use volumetric input, for example, for medical data. Medical data, you take, for example, an MRI device or a CT, and of course you get no color information, but you get densities, and then you can. And this is what the medical device manufacturers do in their software. They detect the tissue type and adjust the optical properties, and they do renderings, for example, to render a heart or so. And if you get the rendering, this information per voxel, if you have the information of the optical properties per voxel, not only the optical properties, could also be mechanical properties or so, then you have much more knowledge, and you do not need to tweak based on information that you have just on the surface. That's a big advantage of volumetric input.
Okay. Okay, you got information not only for the outside, like now, what we consider as input object with the texture map, but also for the inside.
Yeah.
Okay.
Correct. Correct.
Okay. Perfect.
Okay.
Okay. Thank you very much. Are there any questions for Philip? Again, I think only those with the CrabCat software has this cuttlefish desktop license or experience. Okay, if there's no question, we'll go back to the agenda, Marco.
Yes, or we can stay by Philip, I think, because the next presentation.
No, it's actually it's Daniel or Dan Chen who will give the talk.
Ah, okay. Yes, the next talk is the optical printer models for 3D printing.
Yeah.
From who?
And
who would like to be presenter?
Danwu Chen or Daniel Chen.
Got it. Okay.
So maybe one thing before Daniel, before you start, according to our project, we are focusing, or one part of our focus is to use machine learning in order to simulate, or not simulate, in order to predict the color based on learned values. And this is what Daniel will present today. Okay, Daniel.
Yeah, I'm going to show my screen. Can you already see my screen here?
Yes.
Okay.
Looks like this.
Yeah. Yeah. So my name is Danwu Chen. You could call me Daniel. I'm a researcher from the 3D printing department of Fraunhofer IGD. I'm also involved in the European Marie Curie project called Evocation. And my research focuses on applying machine learning to computer graphics, especially color and translucency reproduction for 3D printing. So today my topic is machine learning for optically characterizing 3D printers. So here is the motivation and also the problem. So characterizing of 3D printers is a required process to ensure 3D printers can accurately reproduce color and translucency. And a typical task is shown as follows. Given a material arrangement, say CMYK gamma, we need to predict the color and translucency of the resulting print. So the existing method of characterizing 3D printers is a pure empirical approach. And this approach takes in some already known samples as its own database. And every time it needs to predict on a given material arrangement, CMYK gamma, and it looks up into the database to find the neighbor samples and do linear interpolation on the neighbor samples to get the final prediction. So the problem is that this approach requires many samples to make its database dense enough. Otherwise, the linear interpolation will be non-accurate. So, for example, we could have lots of such kind of samples, and we make it print using a certain kind of printer, and then we measure it using a spectral photometer, and the printing and measuring the printing and measuring efforts could be a lot when it comes to 3,000 samples. So our objective is to significantly reduce the printing and measuring effort without sacrificing accuracy. Or if we spend the same amount of effort, could we greatly improve the accuracy? So we adopt a machine learning approach. And here is the idea. We use a machine learning model, specifically neural network model, to learn the mapping relationship between the input CMYK gamma and the output color and translucency, namely CLAP and also alpha. Alpha here means translucency. And so this approach has two advantages. Firstly, a neural network model can learn very complex mapping relationship between input and output, rather than just making an assumption of linear mapping relationship, as like the traditional method. And secondly, a machine learning approach is learning from data rather than memorizing data, especially memorizing neighbor samples. And in this manner, machine learning approach could be more data efficient.
Daniel?
Yes.
Can you show how you go from CM by gamma to CM by K clear white? Is this a global fixed voxel by voxel transform, or is it also something which is based on the distance to the surface and the neighborhood information? Because this is now 2 dimensions. CM by K are the colorants, and gamma is just a psychophysical correlation. So how do you go from CM by G to the CM by K clear white? Can you just explain?
I can answer this. The gamma is basically a percentage between the white and the clear material mixed in the volume. Which means if you have basically we can reduce the CMYK clear or white and clear into CMYK gamma, because we have to fill always a whole unit volume, right?
Mm-hmm.
So which means if we don't need 6 values to describe the whole volume, because this is the 6th value is just the volume minus the 5 described. And in order to get what we did is because clear and white is neutral, we have used just the term gamma. That so if gamma is 0, then we have no clear material at all. It's just white. If gamma is 100 or 1, then we have no white in the whole print, just clear. And then there's a linear percentage.
And this is a global transform, irrespective of the neighborhood and the distance to the surface. This is a global transform, or is it dependent on where this voxel sits?
No, this is given the material arrangement scheme from the pipeline, which means when we compare this to the approach from ELM, it is not so powerful, because ILM can have whatever kind of arrangement of voxels, and they simulate using Monte Carlo this arrangement. Right? We can just have the arrangement that we give as a we give with a pipeline. So the pipeline, for example, has a distinct half-toning method, and this half-toner is applied, for example, just 2 millimeters to the surface, and then the inner part is just white, for example. Then this model just learns basically this arrangement. It is not learning anything else.
So if I have a specific test chart in a flat arrangement for reading, like a color chart, the recipe would be the same as I would have been this as an outer shape of your body model.
Yeah, it has to be. It has to be the same. Otherwise, it's basically similar to in 2D printing. You have if you use a different half-toning method, right? If you use, for example, green noise half-toning versus blue noise half-toning, then even so your CMYK values are the same, the output looks different, right? And this is similar. So it's a completely it's a way. It's not physical based at all. It just uses some techniques that can learn whatever kind of functions.
For me, it's just important first, is it the global transform, like ICC, you have a to B profile, and it's the same if a pixel is alone with a complete white paper, or if the pixel is in a colorful environment, to have the same foreseeable transform and not something related to neighborhood and relations and something like this, which would make it more dynamic and But this is more predictable. That means if I have a flat arrangement and I characterize a flat arrangement, I can then also predict curved and free shape arrangements.
Yes.
Perfect. Okay, good. Yeah. So sorry, Daniel.
Yep. So this is the whole framework. So at the beginning, the whole system, the input for the whole system is the CMYK gamma, and the output of the whole system is the color and translucency, namely D-lab and alpha. So in this system, we have a neural network model to learn from CMYK gamma to spectral and alpha. Spectral here means we use 31 wavelength measurements, which is from a spectral photometer. The measurement wavelengths length ranges from 400 nanometer to 700 nanometer. So this is 31 measurements. So for this framework, it can not only predicts the final wanted color and translucency, but it also predicts the spectral prediction. So the spectral prediction could be useful for some applications such as 3D soft proofing. So here is the structure of the neural network. So basically, it has 7 layers, and at the beginning is the input layer with 5 neurons corresponding to CMYK gamma, 5 features, and then at the end it's the output layer with 32 neurons corresponding to spectral and alpha. And in between the input layer and the output layer, there are 5 layers. With each layer has either 200 neurons or 1,500 neurons. So basically, this is a multi-layer, fully connected neural network. And in this network, we enable nonlinearity by using rectified linear unit activation function, or say ReRU. And this is important because we think the mapping relationship between the input CMYK gamma and the output spectral and alpha could be nonlinear. And so we use the ReRU activation function for hidden layer, for all the hidden layers. And we also use dropout as a regularization technique to reduce overfitting. And because we know that a neural network could be performed to overfitting, so a suitable regularization technique is important here to avoid overfitting. And when it comes to evaluating the model performance, we always use the held out unseen test data, which means the test data is never seen during the training process, and it's only be used after we have trained the model, so that we could get a reliable performance evaluation. And also we use cross validation, which means we repeat the whole training and the evaluation multiple times, and we get the average performance as the final performance, so that we could get a reliable performance evaluation. Okay. So here is the experiment setup. In our data set, we have 3,125 samples printed by Stratasys J750, and we have these samples measured using a Barbaria spectral photometer, and then we get not only the samples but also the ground truth of spectral and alpha. And for training, we use 90% of the data for training and 6% for validation, which is used to do parameter tuning and also model selection, and the remaining 4% for testing. And this is random splitting. And we know that here the number of testing samples is much less. It's much less, so we use cross validation. For example, 10 folds, and that is to repeat the independent random experiments so that we could get the average as the final model performance evaluation, and that way we could get a more reliable performance evaluation. And the model is trained on NVIDIA 2080 Super GPU. So here is the model performance on unseen test data. Here I compare machine learning versus the traditional method. For the image, for the figure on the left side, it shows the average prediction error in terms of CD2000, because we can predict the CLAB, then we could compare the prediction versus the ground truth, then we get the CLAB 2000. So this figure shows the average error. The horizontal axis is the number of training samples, which ranges from roughly 200 to 3,000, and the y-axis is the average error. The orange one is from the traditional method, and the blue one is from machine learning. And you can see from the trend here that as the number of training samples increase, the prediction error goes down. While for the traditional method, it can reach at most error at roughly 3. While to achieve a similar result from machine learning, it requires only 10 times less data. While on the other hand, if we use all of the data, which corresponds to the final point of these two curves, the accuracy can be improved by 6 times. And let's look at the figure on the right side, which shows the 90th percentile of the prediction error. So here, we could also see a similar trend here. But the thing is that the traditional method can achieve at most error at 6. And while the machine learning method can achieve a much less error. And the problem is that in real industrial application, we could assume a typical tolerance equal to 2 in terms of CD2000, while for this typical tolerance, the traditional method has a much higher error than the typical tolerance. While for machine learning, it could achieve this goal with roughly only 900 samples, and still with some space as we increase the number of training samples. So this suggests that the machine learning approach could be more feasible or practical for real industrial application. Here is the standard deviation of error, prediction error. So you could see from here that the machine learning approach could has roughly 6 times smaller standard deviation, and this means machine learning approach is more stable than the traditional method. This slide shows some spectral predictions on some test samples. These samples are randomly selected. So each square corresponds to a single sample, and y-axis, the horizontal axis is the 31 wavelength, and y-axis is the measurements. The black dot is from the ground truth, and the blue line is from the machine learning prediction. You could see here that the machine learning prediction match quite well with the ground truth. And let's look at some worst test samples whose prediction error is the biggest. We could see here in the circles there is some slight offset between the ground truth and the prediction, but on the whole, the prediction still match quite well with the ground truth, and this prediction could be useful for 3D soft proofing. Okay, if we care about color without considering translucency, then we could reduce the required number of samples from 3,000 to roughly 600. So again, in this slide, I show I compare the machine learning approach versus the traditional method, and you could see the left figure here. The orange one is from the traditional method. You could see that it could achieve average error at most roughly 3.3 or 2. And while to achieve similar result, the machine learning approach only require 5 times less data. And in terms of accuracy, machine learning could achieve 5 times improvement. And from the figure on the right side, it's the 90th percentile prediction error. And you could also see that for the typical tolerance, which we assume to be 2.0, the traditional method cannot achieve this goal unless we collect much more data. But the machine learning could achieve this goal with only 300 samples. Okay, so in an ideal situation, we want to train a machine learning model on one printer and then use it for any other printers. While the reality is that there is inter-printer variability, which could be 2.0 on average in terms of 32,000 color difference. And this means a model train on the data of printer 1 doesn't work well on printer 2, even they are of the same type. For example, so this is J750 that we used. So here we have a model trained, which is trained on the data from printer 1, and this model can predict quite well on test data of printer 1. So you can see here, the average error, prediction error is 0.6, and the 90th percentile of prediction error is 1, which is very small. While if you use this model directly to predict on printer 2, the error goes up drastically. And you can see here, the average error is 3. The 90th percentile is roughly 6. This is big. So what can we do? So shall we directly throw away the old model and collect another 3,000 samples to train a new model? Well, this will be quite expensive. So instead of that, we could use the boosting strategies. We could still use the old model, but boost the old model with new data from printer 2. So here is the idea. We already have a pre-trained model on printer 1 using 3,000 samples, and we have a smaller amount of data from printer 2, say 500. We can use the old model to predict on these 500 samples to get a reference for printer 2. We say reference because we cannot use it directly as the prediction, because we know due to the inter-printer variability, the model doesn't predict very well on printer 2. So we use it as a reference even though this prediction is not very accurate, but it's still close. It's still similar to the ground truth, because even those printers, they are different, but they still share some similarities. So the knowledge learned from printer 1 could be still useful for printer 2. So this is the main idea. So we get a reference here, and this reference, definitely there is a residue error between the reference and the ground truth. So we train another model to only predict the ground truth. Sorry, only to predict the residue error, which we call offset here. It's equal to ground truth minus the reference. So we train this new model based on the 500 samples from printer 2 to only predict the offset, to only compensate the offset. And by combining them together, by summing them together, we end up with the approximation of the ground truth. So let's see the result. This table shows the result of the performance of different models on printer 2. So previously we have a model from printer 1 as a reference. So if we directly take it as the final prediction, we have error as big as 3. While if we completely throw away printer 1's model and retrain on the 500 samples from printer 2 from scratch, we get an average error at 2 and P90 roughly 4. But if we use the boosting strategy, by summing up the reference and the offset, we could reduce the average error from 2 to 1.6 and reduce the 92th percentile from 4 to roughly 3. So this enables us to achieve a better accuracy by using a small amount of data from the new printer. Okay, this is a summary. So I've showed that the traditional characterizing method requires lots of printing and measuring efforts, and the machine learning approach can reduce number of samples by 10 times or improve accuracy by 6 times. And when it comes to color only, the improvement is roughly 5 times. And secondly, the machine learning approach predicts not only color and translucency, but also it predicts the spectral, which could be useful for 3D soft proofing. And finally, we show a boosting strategy that could boost an old model with a smaller amount of data from a new printer by transfer the knowledge learning from one printer to another printer to enable small data. So this is the future work. We would like to extend the boosting strategy, transfer learning strategy for geometrical calibration, especially considering a scenario that where the appearance of a sample printed horizontal could be very different from the same samples printed vertically. So in this scenario, we think the transfer learning could be promising because whether the samples is printed horizontal or vertically, they still share some similarity. The color or appearance will is still similar. So we could transfer the knowledge from one model to from one orientation to another orientation. So the second possible future work is applying the boosting transfer learning strategy between different types of printers. For example, could we learn from J750 and then transfer it to J7 35 were even transfer from psoriasis printers to other companies' printers. While this, we are still considering whether this is meaningful. This could bring some this is worth efforts to get some benefits. So we are also interested in your opinions. Maybe you could also provide some your views, your expert views. Yeah. So that's it.
Thank you very much, Daniel. Which framework did you use? Can you say about the network or the framework you're using?
Yeah. So the framework is TensorFlow and Keras.
And how did you match the delta transparency? Did you measure it like in the paper from Philip and did the Euclidean distance, or is it just the delta in color which you objectify?
You mean the how to compare the graduate and
the translucency? You know, we have a two color reference color and a predicted color, and you have a delta E, and you have a predicted translucency and a measured or a given translucency. How do you objectify the closeness of translucency reproduction?
For translucency, we use the absolute error.
And then the maximum of the absolute error, because we have not seen any statistics here about the translucency error.
Because we have we predict both the spectral and alpha, and for spectral we use we convert it to the color space and calculate the Psi 2000, while for alpha we directly calculate the delta, the absolute error.
Yeah, I understood, but I haven't seen about it. I haven't seen any statistics about the absolute error of the translucency here. Is it the same magnitude with color, or?
Sorry, could you repeat your question again?
You know, the color differences are magnificent. The performance with respect to model it with respect to close color match is very, very amazing. But you also try to match and predict translucency. How good is your translucency accuracy? So I did not see any.
Okay, yeah. I have a spare slice. Let me show you. So this is from one of the models. So for translucency, the average error is 0.004, and P90, I mean the 90th percentile is roughly 1%, or say 0.01.
Okay. That also
I think it's also important to put this into perspective. These values are below, at least for these reference materials that we describe in our paper, which has isotropic phase function and just vary in absorption and scattering without being completely independent of the wavelengths. For these reference materials, these values are below the visual, just the J and E in translucency.
So also amazing.
I mean, this is the translucency is quite simple. It's not, because it's not changing a lot actually. The printing systems have a quite small translucency gamut, and which means that there's not so much variation in possible in terms of translucency by the printing systems.
Okay. We have Yoav. You have to just unmute yourself and ask a question. I see you have your raised hand.
Okay, I
Okay.
managed to unmute myself at last. Okay, first a comment about the question in the end. I do recommend the exercise of transferring from one Stratasys printer to another. I have a very good experience with that. It works well. I never used neural networks. I used traditional methods. Especially with the new printers, we have new small format printers coming out. For one, the J55 as a round plate, and I think it will be very difficult for people to print plates with a great number of patches to do the characterization on the round plate. So it will be a good exercise printing a small number of patches with that small printer, and then doing some transfer from a larger printer. I think it will work well. Now I have quite a lot of questions. I don't know if you have time to answer them all. First of all, the traditional method that you're comparing with, what was it? Second, in the boosting, you have you adding the output of one network to another. Could you do it by cascading or multiplying, applying the second network to the output of the first? And last question is, could the second smaller network in the boosting be replaced with the traditional method?
So yeah, so for the first question, the traditional method is based on simple linear interpolation. So which means it takes in already some known samples, and then it every time it comes a new sample to be predicted, this approach will take the neighbor samples to do linear interpolation to get the prediction.
Maybe I can comment one thing to this. It's basically the cellular Neugebauer. Cellular Neugebauer method that is used here. You know, it's like multilinear interpolation of the Neugebauer primaries, or if you use more cells, you need a regular grid and do an interpolation. In MATLAB, it's interp n.
Thank you.
Okay.
Yeah, you can also answer the other question, if you can.
Yeah. So for the boosting method, here we only take the so what are you the last two questions?
The second question was, can I put the smaller second boosting network at the output of the first one to cascade them? Maybe it will give me a better result. And the last question is, can I replace the second network with some kind of a classical method, like some kind of a function or a matrix?
Mm-hmm. So for the second question, do you mean that we could connect these two models in the line to get the final prediction in a way to combine them together?
Yes, to train the second one to get the output of the first and give the desired output.
I think by combining them together in one line is kind of difficult. So I think it's more feasible to separate them, because one is trained on data from printer 1 and the other instrument from printer 2, and actually usually we could have an old model far earlier than the new data comes from printer 2. So when printer 2 comes, we could, maybe I think the typical scenario is that we already have the model already trained it, so we can just use it as to predict the reference, and then use the new data to predict the remaining residual error. So that way we could combine them together. And for your first question, I think, yeah, definitely we could replace the second small model with traditional method. But again, it goes back to the situation that the data efficient, because if you compare the machine learning with the traditional method, even we use a small amount of data, the performance is hugely different. So I prefer using neural network, but I think other models are also possible, especially if we could combine them together to do things like ensemble learning by combining the traditional method and also the neural network method. So by combining them together, maybe we could also achieve a better result than each of them.
Oh, okay, thank you. We are a little bit over the time, but we are already done with this topic. Thank you for your presentation. And we go to the last point. I want to introduce the people here, but I think a lot of people are from this project attendees here, but not all. So we are happy. We are a member, partner, not partner, beneficiary of this Appeals project. It's Horizon 2020 project from the European Union. And the goal is to train 15 PhD students in appearance printing using 3D and 2.5D techniques, and the appearance matching of with originals to the printed ones. And in this slide, you see the main work packages. The main topic work packages is work package 2. This is the measurement of the BSS-RDF, the bidirectional surface scattering reflection distribution function, I think.
It's a tongue break, or yeah.
And the corresponding visual attributes like gloss, transparency, scattering, and so on. We have hear a lot about this topic today. Then chromatism, 3D halftoning, and material light interaction. This is work package 3, and work package 4, representing and communicating material appearance, and work package 5 are the methodologies for 2.5D and 3D printing application. And we have in Fogra, we have one early stage researcher here, Donatella Saric, and you are part of which work package?
Work package 4.
Work package 4.
Yeah.
And a lot of people from this project are attendees today, and this is the overview structure about the topics of these people.
You can wave at the camera to say hello.
And the main goal, we are a little bit over time, I have to skip this a little bit. We go from in printing from only from gamut mapping with colors to appearance mapping. Yes, and not only the mapping of a diffuse color, you have also to map the translucency, like Philip Urban with this alpha channel we have seen. And in future, we want to do this perceptive with the gloss. And the working title of Donatella here is to develop a method to measure and communicate and print this gloss. And okay, that was very short, but isn't over the time.
Okay.
That's one point is now over. We planned a Munich 3D forum on 15 October this year, and we will cancel this this event because of COVID-19. It's not possible or not so easy to make such a symposium or forum here in Fogra. And so we make on this day another project meeting to these two topics, like the graphical 3D printing, the Softproof, and for the second research project in 3D color modulation. And
save the date.
Save the date, and we hope we can meet in Fogra then in October.
Hopefully face to face.
Hopefully face to face. Yes, for Softproof it's very good.
Yeah.
Face to face. Okay, then thank you for our attention.
Is there any other business or something people would like to add or say before we close the meeting? So the last chance, raise your hand or make your contribution. If that is not the case, we can adjourn the meeting.
Okay, then thank you for
your contribution and participation, and talk to you later.
Bye.
Thank you.